Everything you have been told about black holes is almost correct. They swallow stars. They trap light. They bend spacetime so violently that even time itself seems to hesitate near their edges. If you cross the event horizon, there is no turning back. No signal escapes. No message returns. From the outside, whatever falls in is gone forever. That part is real. Black holes are not myths. They are not speculative mathematics. We have imaged their shadows. We have detected the gravitational waves from their collisions. We have watched stars orbit something invisible and impossibly dense at the center of our galaxy. They exist. But what we think they do may not be the full story. For decades, black holes were treated as the universe's ultimate shredders. Drop anything in matter, radiation, even entire solar systems, and it would be reduced to something indistinguishable. From far away, the black hole would settle into a simple state described by only 3 numbers: its mass, its electric charge, and its spin. Everything else was erased. It did not matter whether the black hole formed from a dying star, a collapsing galaxy, or a library containing every book humanity ever wrote. Once the matter crossed the horizon, all details were lost. The complexity of the original system vanished behind a smooth surface of pure gravity. This idea was not philosophical. It was mathematical. General relativity, Einstein's theory of gravity, describes black holes as simple, elegant, featureless from the outside. The details of what falls in do not affect what comes out. And what comes out, according to classical thinking, is nothing. But then quantum mechanics entered the picture. Quantum mechanics is not just another theory. It is the most precisely tested framework in the history of science. Every experiment performed at microscopic scales confirms its predictions to astonishing accuracy. And quantum mechanics contains a rule that is absolute. Information is never destroyed. Not blurred beyond recovery. Not deleted from existence. Not erased from reality. If you know the exact quantum state of a system at one moment, the equations allow you to determine its state at any other moment, past or future. The evolution is reversible, complete, deterministic in its structure, even when outcomes appear probabilistic. This property is called unitarity, and it is not optional. If unitarity fails, the entire foundation of quantum theory collapses. So here is the problem. Imagine throwing a perfectly ordered system into a black hole. A carefully arranged configuration of particles. A specific quantum state. According to general relativity, it disappears behind the horizon and eventually reaches the singularity, a region where spacetime curvature becomes extreme beyond description. From the outside, nothing about the black hole reveals what fell in. According to quantum mechanics, that precise configuration cannot simply vanish. It must still exist in some encoded form within the total state of the universe. These two statements cannot both be true, at least not in the way they were originally understood. And the contradiction did not remain theoretical for long. In 1974, Stephen Hawking made a discovery that transformed black holes from cosmic vacuum cleaners into thermodynamic objects. He showed that black holes radiate. Through quantum effects near the event horizon, black holes slowly emit particles. This radiation carries energy away. Over incredibly long timescales, a black hole shrinks. Eventually, it evaporates completely. That discovery alone was revolutionary. But it created a far deeper crisis. Hawking's calculation showed that the radiation emitted by a black hole is purely thermal. Random. Featureless. It carries no information about the matter that formed the black hole or fell into it. If that is true, then when a black hole evaporates, all the information about everything it consumed is gone. Not hidden. Not recoverable. Gone. That conclusion stunned the physics community. Because if information can be destroyed in black holes, then the universe is not fundamentally predictable. The future would not be fully determined by the present. Quantum mechanics would be incomplete. And if quantum mechanics is incomplete at that level, then every field built upon it, from particle physics to chemistry to condensed matter, would stand on uncertain ground. The implications are not abstract. They cut to the core of what we mean by physical law. When we say the universe follows laws, we mean that its evolution is consistent. That given enough information, the future is determined by the present. That nothing simply vanishes without trace. But black holes seemed to violate that principle. They appeared to be cosmic forgetting machines. To understand how radical this is, imagine writing down the exact quantum description of a system. Every particle, every field, every correlation. That description is the most complete account of physical reality available. Now imagine that description falling into a black hole. If the black hole evaporates into random radiation, the final state of the universe no longer contains enough information to reconstruct the original state. The chain of physical causation is broken. Reality has lost something. And physics, at its deepest level, does not allow that. So the question became unavoidable. Do black holes truly destroy information? Or have we misunderstood what black holes are? For years, the debate raged. Some physicists accepted Hawking's conclusion. Information is lost. Quantum mechanics must be modified. Others refused to accept that possibility. Information must somehow escape, encoded subtly in the radiation. The disagreement was not about details. It was about the foundations of reality. If information is lost, then the universe has an intrinsic randomness that no deeper law can remove. If information is preserved, then black holes are not endpoints. They are transformations. And that transformation must be encoded in ways we do not yet fully understand. Over the decades, this paradox has driven some of the most profound ideas in modern physics. The concept of black hole entropy, that a black hole's information content is proportional not to its volume, but to the area of its surface. The holographic principle, the idea that all the information contained in a region of space might be encoded on its boundary. The suggestion that spacetime itself may emerge from deeper informational structures. These are not small adjustments. They are tectonic shifts. Because if information is more fundamental than matter, then matter itself may not be the base layer of reality. Perhaps what we call particles are patterns in something deeper. Perhaps what we call spacetime is not fundamental. Perhaps the universe is not built from things, but from relationships, correlations, encoded structure. Black holes sit at the center of this realization. They appear to destroy everything. But they may instead reveal that nothing truly disappears. Matter can collapse. Stars can die. Galaxies can merge. But the informational content, the precise configuration that defines reality at each moment, may be preserved without exception. That idea is both unsettling and extraordinary, because it means the universe never forgets. Not in memory, not in narrative, but in the strict, physical sense that every quantum state leaves an imprint on the total structure of reality. Black holes do destroy matter. That much is true. They crush it beyond recognition. They hide it behind horizons we cannot cross. But the deeper question is not about matter. It is about information. And if information is never lost, then black holes are not cosmic erasers. They are something far more mysterious. They are guardians of the most fundamental rule in physics. That reality, at its deepest level, remains consistent. And understanding how that consistency survives the most violent objects in the universe may force us to rethink what the universe is actually made of. This is the journey ahead. From collapsing stars to evaporating horizons. From thermodynamics to quantum entanglement. From apparent destruction to hidden preservation. Black holes may destroy matter. But the universe does not forget. And discovering why may change how we understand reality itself. For most of the 20th century, black holes were not paradoxes. They were not philosophical puzzles. They were not threats to the foundations of physics. They were solutions. They emerged naturally from Einstein's equations, elegant, mathematically clean consequences of gravity taken to its logical extreme. To understand why they appeared so straightforward, we have to return to 1915. When Einstein introduced general relativity, he replaced Newton's invisible gravitational force with something more profound, geometry. Gravity was no longer a pull between masses. It was the curvature of spacetime itself. Mass and energy deform the fabric of spacetime. Objects move along the curves that deformation creates. The Earth orbits the Sun not because it is being pulled by a force in the classical sense, but because it is following the curved geometry around a massive body. This was a radical conceptual shift, and yet the mathematics worked. Mercury's orbit, previously unexplained by Newtonian theory, matched Einstein's predictions precisely. Light bending around the Sun during an eclipse confirmed spacetime curvature. General relativity was not just philosophical beauty. It was correct. Within a year of Einstein publishing his field equations, Carl Schwarzschild found an exact solution describing spacetime around a spherical mass. It was a stunning achievement. And buried inside that solution was something deeply strange. At a specific radius, later called the Schwarzschild radius, the equations implied that escape velocity exceeded the speed of light. At that boundary, light could no longer travel outward. This radius defined what we now call the event horizon. At first, physicists were skeptical. The mathematics seemed to blow up at the horizon. Certain terms became infinite. The metric appeared singular. But over time, it became clear that the apparent singularity at the horizon was merely a coordinate artifact. With the right mathematical description, the horizon was smooth. Nothing physically infinite happened there. The true singularity lay deeper, at the center. And that singularity was different. Unlike the horizon, it could not be removed by changing coordinates. Curvature invariants diverged. Space-time itself appeared to end. But for decades, this was treated as a mathematical boundary, not necessarily a physical one. Because something else became more important. Astrophysics. By the mid-20th century, it was clear that massive stars could not remain stable forever. Nuclear fusion provides outward pressure. When fuel runs out, gravity wins. 4 stars significantly more massive than our Sun, no known force, not electron degeneracy pressure, not neutron degeneracy pressure, can halt total collapse. The result is inevitable. The star implodes. If the mass is high enough, collapse continues beyond the neutron star stage. The Schwarzschild radius forms. An event horizon appears. And once that horizon forms, something profound occurs. From the outside, time appears to slow for the collapsing matter. Light escaping from near the horizon becomes increasingly redshifted. Signals grow weaker and slower. To a distant observer, the infalling matter seems frozen at the edge. But this is only an external illusion. For the matter itself, crossing the horizon is uneventful. There is no surface. No flash. No barrier. It simply passes a boundary beyond which escape is impossible. Inside the horizon, all future directed paths lead inward. Not because of force. Because of geometry. The radial direction becomes time-like. Moving toward the center is as inevitable as moving toward tomorrow. This was not speculative philosophy. It was the unavoidable conclusion of Einstein's equations. And here is what made black holes appear conceptually simple. No matter what formed them, once they settled down, they were described by only 3 numbers. Mass, charge, spin. That was it. This result, formalized through a series of mathematical proofs, became known as the no-hair theorem. Black holes have no hair. No distinguishing features. No detailed memory. If 2 black holes share the same mass, charge, and angular momentum, they are indistinguishable from the outside. It does not matter whether one formed from a collapsing star and another from the merger of 2 neutron stars. It does not matter whether a library, a planet, or a perfectly ordered crystal fell into one of them. All complexity disappears behind the horizon. This felt consistent with physical intuition. After all, physics regularly reduces complexity. Burn a book, and its molecular structure becomes ash and gas. Explode a star, and its internal structure becomes plasma and radiation. Order becomes disorder. Structure dissolves. Black holes seemed to represent the ultimate extension of this process. They were gravitational entropy machines. They took structured matter and reduced it to gravitational simplicity. And because nothing escapes the horizon, no information about internal structure returns to the outside world. Classically, this was not alarming. In classical physics, information was not treated as a conserved quantity. Energy is conserved. Momentum is conserved. Charge is conserved. But information, it was not considered fundamental. If details became inaccessible, that was simply a practical limitation, not a violation of law. The interior of a black hole was causally disconnected from the exterior. Signals could not travel outward. So even if internal structure remained, it was irrelevant to the external universe. The black hole evolved according to deterministic equations. Mass increased as matter fell in. Spin changed according to angular momentum transfer. Charge neutralized quickly through interaction with surrounding plasma. Externally, the system remained fully predictable. There was no paradox, no crisis, no foundational instability. Black holes were extreme but orderly. They were the final stage of stellar evolution, the gravitational graveyards of massive stars. And over time, astronomical evidence confirmed their existence. X-ray binaries revealed compact objects too dense to be neutron stars. Stars orbiting the center of the Milky Way traced precise ellipses around something invisible and enormously massive. Gravitational waves from merging black holes matched general relativity's predictions almost perfectly. Every observation reinforced the classical picture. Black holes were real. They behaved as expected. They absorbed matter. They emitted nothing. They settled into simplicity. They destroyed structure. And that destruction did not appear to violate any physical law. Because classical physics did not demand that information survive. It demanded only that energy and momentum balance. Within that framework, black holes were not mysterious destroyers of reality. They were elegant endpoints of gravitational collapse. They were confirmation that Einstein's theory worked even in the most extreme conditions. They were dramatic, but not destabilizing. It took quantum mechanics, and the realization that black holes are not entirely black, to change that. But before we go there, it is important to appreciate something. The classical picture was not wrong. It remains astonishingly accurate for describing black holes from the outside. Event horizons exist. Spacetime curves exactly as predicted. Gravitational waves match calculations. Accretion disk dynamics align with theory. The simplicity is real. What was incomplete was not the geometry. It was the deeper layer beneath geometry. Because classical general relativity describes spacetime as smooth and continuous. Quantum mechanics describes reality as fundamentally granular and probabilistic. And when these two frameworks meet, at the horizon of a black hole, something unexpected emerges. The apparent simplicity begins to hide a deeper complexity. But before that collision between theories, black holes were understood as ultimate destroyers of structure. They crushed matter beyond recognition. They hid complexity behind horizons. They erased visible history. And from the outside, they revealed nothing except mass, charge, and spin. That was the settled understanding. That was the stable picture. That was what we thought black holes were. And it seemed complete. Until it wasn't. For decades, black holes were gravitational objects. They belonged entirely to general relativity. They were cosmic-scale phenomena, described by curvature, geometry, and the mathematics of spacetime. Quantum mechanics, by contrast, ruled the microscopic world. Atoms, electrons, photons. It governed the behavior of particles and fields at the smallest scales, where probabilities replace certainties and energy comes in discrete packets. For much of the 20th century, these two frameworks existed in parallel. General relativity described planets, stars, galaxies. Quantum mechanics described atoms and radiation. And although physicists knew the two theories were fundamentally incompatible in their mathematical structure, the incompatibility rarely caused practical trouble. The scales were too different. Gravity is extraordinarily weak compared to the other fundamental forces. At atomic scales, gravitational effects are negligible. At cosmic scales, quantum fluctuations average out. The universe seemed neatly partitioned. Until someone asked a simple question. What happens when quantum fields exist near a black hole? This was not a speculative question. Quantum field theory, the framework combining special relativity and quantum mechanics, tells us that empty space is not empty. Even in vacuum, quantum fields fluctuate. Particle-antiparticle pairs momentarily appear and annihilate. Energy briefly manifests and disappears, constrained by the uncertainty principle. In ordinary conditions, these fluctuations are invisible. They average out. They leave no permanent trace. But near an event horizon, something subtle changes. In the early 1970s, Jacob Bekenstein made a bold proposal. He suggested that black holes should have entropy. This idea was radical. Entropy is a measure of disorder. It counts the number of microscopic configurations corresponding to a macroscopic state. If a system has entropy, it must have internal degrees of freedom. It must possess microstructure. But black holes, according to classical general relativity, had no internal structure accessible from the outside. They were defined by only three parameters: mass, charge, spin. Nothing else. So how could they have entropy? Bekenstein argued from thermodynamics. The second law of thermodynamics states that entropy in a closed system never decreases. If you throw a box of hot gas into a black hole, the entropy of that gas disappears from the observable universe. To preserve the second law, the black hole itself must gain entropy. And the only quantity that seemed to increase in a way resembling entropy was the area of the event horizon. The larger the black hole, the larger its surface area. So Bekenstein proposed that black hole entropy is proportional to horizon area. Not volume. Area. This was strange. In every other physical system, entropy scales with volume. But here, it scaled with surface area. It was an anomaly. At first, many physicists were skeptical. Entropy implies temperature. And temperature implies radiation. If black holes had temperature, they must emit something. But classical general relativity insisted that nothing escapes. The event horizon is absolute. No radiation can emerge. The idea that black holes radiate seemed absurd. Then Stephen Hawking performed the calculation. He did not set out to prove Bekenstein right. In fact, he expected to disprove the idea. But when Hawking analyzed quantum fields near the event horizon, something astonishing appeared in the equations. Black holes radiate. Not metaphorically. Literally. Quantum effects near the horizon produce a steady emission of particles. From a distant observer's perspective, the black hole emits thermal radiation with a temperature inversely proportional to its mass. The larger the black hole, the colder it is. The smaller the black hole, the hotter it becomes. This radiation is now called Hawking radiation. And its implications were devastating. Because if black holes radiate, they lose energy. If they lose energy, they lose mass. If they lose mass, they shrink. And if they shrink long enough, they eventually evaporate entirely. The gravitational graveyard was no longer permanent. Black holes were not eternal. They had lifespans. For stellar mass black holes, that lifespan is longer than the current age of the universe by many orders of magnitude. But in principle, evaporation is inevitable. And this is where the crisis begins. Hawking's calculations showed that the radiation emitted is purely thermal. It has no structure, no imprint of what fell into the black hole. It depends only on mass, charge, and spin. The radiation is random, featureless. It carries entropy, but not information about the specific configurations that formed the black hole. Now consider what this means. Imagine throwing a complex system into a black hole. A precisely arranged set of quantum states. Perhaps a book encoded in particle configurations. Or a star with intricate internal structure. According to classical theory, that structure disappears behind the horizon. According to Hawking's quantum calculation, the radiation emitted during evaporation is thermal. It contains no record of the original state. When the black hole finally evaporates, all that remains is a cloud of random radiation. The original information appears gone. Not hidden. Not scrambled. Destroyed. This was not a philosophical concern. It was a mathematical contradiction. Quantum mechanics demands that evolution of a closed system is unitary. That means the total information contained in the wave function must be preserved. If you know the exact quantum state at one time, you can, in principle, compute it at any other time. The equations do not allow information to vanish. But Hawking's results suggested exactly that. Information falls in. Random radiation comes out. The mapping between initial and final states is not reversible. Different initial states could produce identical final radiation. The universe would lose memory. This became known as the black hole information paradox. And it was not a minor puzzle. It was a fundamental inconsistency between two pillars of physics. General relativity allowed information to disappear behind the horizon. Quantum mechanics forbade information destruction. One of them had to give. For a time, Hawking himself argued that information truly is lost. He suggested that black holes cause quantum evolution to be non-unitary, that the laws of quantum mechanics would need modification in gravitational contexts. This was a shocking claim. Quantum mechanics had survived every experimental test with extraordinary precision. To modify it would undermine the foundation of particle physics, chemistry, condensed matter theory, nearly everything. Most physicists were unwilling to accept that. They believed the error must lie in the semi-classical approximation Hawking used, treating spacetime as classical while quantizing fields upon it. Perhaps the full theory of quantum gravity would resolve the paradox. Perhaps information is not lost. Perhaps it escapes in subtle correlations within the radiation. But how? The radiation appeared thermal, random, featureless. Where could the information hide? Some proposed that information remains trapped in a remnant, a tiny stable object left behind after evaporation. Others suggested that subtle correlations in Hawking radiation preserve information, though hidden within entanglement patterns too delicate to see. Still others began to suspect something even more radical. Perhaps spacetime itself is not fundamental. Perhaps the event horizon is not what we think it is. Perhaps information is encoded on the boundary in ways general relativity does not reveal. The crisis forced physicists to confront something deeper. Black holes were no longer just gravitational endpoints. They were laboratories for the unification of quantum mechanics and gravity. They revealed that our understanding of either theory alone was incomplete. The classical picture had been elegant, stable, self-consistent. But once quantum mechanics entered the horizon, that stability fractured. Black holes were no longer simple. They were battlegrounds. And at stake was not merely the behavior of collapsing stars. It was the consistency of physical law itself. Because if black holes truly destroy information, then the universe is fundamentally unpredictable. And if the universe is fundamentally unpredictable at that level, then the concept of physical law changes. The paradox does not tell us which theory is wrong. It tells us something deeper. It tells us that the way we currently combine them is insufficient. Black holes destroy matter. That remains true. They crush structure. They hide complexity. But the question is no longer whether matter survives. The question is whether information does. And that question reaches deeper than gravity. It reaches into the nature of reality itself. The black hole information paradox was not merely a disagreement. It was a collision. Two of the most successful theories ever created were now pointing in incompatible directions. General relativity had passed every large-scale test thrown at it. Quantum mechanics had passed every microscopic test ever devised. Neither was speculative. Neither was fragile. And yet when combined at the edge of a black hole, they seemed to contradict each other. To understand the depth of the problem, we need to clarify something subtle. Information, in physics, does not mean knowledge in the human sense. It does not mean awareness, memory, or narrative. Information refers to the precise quantum state of a system, the complete specification of all amplitudes and correlations describing it. If you have that full quantum description, you have everything. The positions, momenta, spins, phases, entanglements. The entire physical reality of the system. Quantum mechanics tells us that the evolution of this information is unitary. Unitarity means that the mathematical transformation connecting past and future preserves total information. No two distinct quantum states can evolve into the same final state. The process is reversible in principle. Even if it is practically impossible to reverse, the equations allow it. This reversibility is not a philosophical preference. It is built into the structure of the Schrödinger equation. If unitarity fails, probability conservation fails. If probability conservation fails, predictive power collapses. Now consider what Hawking radiation implies. Hawking's calculation treated spacetime classically but quantized the fields around it. Pairs of virtual particles form near the event horizon. One falls in. One escapes. To a distant observer, this appears as radiation emitted from the black hole. The radiation has a thermal spectrum. That word, thermal, is the problem. Thermal radiation contains entropy but no detailed memory of the source's microstate. It depends only on macroscopic properties like temperature. A hot piece of coal emits thermal radiation. But from that radiation alone, you cannot reconstruct the exact molecular arrangement of the coal before it burned. Now imagine that the coal was replaced with a highly structured quantum system. If it burns, the information is not lost. It is scrambled. Encoded in correlations between emitted photons, surrounding air molecules, and environmental interactions. In principle, if you tracked every particle precisely, you could reconstruct the original state. But Hawking radiation appeared different. It did not carry subtle correlations encoding the black hole's interior state. It was calculated to be exactly thermal. If the black hole evaporates completely into thermal radiation, the initial quantum state has no recoverable imprint. This is not scrambling. This is erasure. And that is forbidden. The paradox sharpened. If general relativity is correct and event horizons behave exactly as described, then information cannot escape. If Hawking radiation is truly thermal, then information is destroyed. If information is destroyed, quantum mechanics must be modified. And modifying quantum mechanics would require rethinking nearly everything built upon it. Some physicists took Hawking's side. Perhaps gravity introduces fundamental non-unitarity. Perhaps black holes are places where quantum coherence ends. But this position carried immense cost. Quantum field theory, the standard model of particle physics, atomic physics, chemistry, all rely on unitarity. Abandoning it would unravel decades of success. Others argued the opposite. Quantum mechanics must be preserved. If so, Hawking's semi-classical calculation must be incomplete. Perhaps the radiation is not perfectly thermal after all. Perhaps subtle quantum correlations, invisible in the original approximation, encode the information. But how could this happen? The event horizon appears to block any escape. Information inside cannot causally influence the outside. Unless something about the horizon itself is misunderstood. This realization began to shift the discussion. Maybe the horizon is not a simple boundary. Maybe it is more like a dynamic membrane. Maybe information is somehow stored on the horizon. This line of thinking led to one of the most profound ideas in modern theoretical physics, the holographic principle. But before we reach that, consider the emotional impact of the paradox on the physics community. For decades, black holes were elegant confirmations of general relativity. Now they were threatening the consistency of quantum theory. The crisis was not just technical. It was philosophical. Physics had operated under a core assumption. The universe is fundamentally consistent. Different theories describing different regimes must agree where they overlap. But black holes revealed a regime where they did not. The paradox became a symbol of the unfinished unification between gravity and quantum mechanics. And it exposed something else. Our intuitive understanding of space and time might be incomplete. Because the paradox hinges on the assumption that space-time behaves classically at the horizon. Hawking's calculation treated space-time geometry as fixed while allowing quantum fields to fluctuate upon it. But in a full quantum gravity theory, space-time itself must fluctuate. The horizon might not be a sharp classical surface. It might be a quantum object. If spacetime is emergent, arising from deeper quantum informational structures, then the horizon could encode information in ways classical geometry cannot capture. This possibility opened entirely new directions. Perhaps black holes do not destroy information. Perhaps they are the key to understanding how spacetime itself is built from quantum information. The debate intensified in the 1990s. String theory entered the picture. In 1996, Andrew Strominger and Kamran Vafa performed a calculation within string theory that counted the microscopic states of certain supersymmetric black holes. Their result matched Bekenstein's entropy formula exactly. This was stunning. It suggested that black hole entropy corresponds to actual microstates. Real quantum configurations. Not abstract bookkeeping. If black holes have microstates, they are not featureless. They have structure. Structure implies information capacity. And information capacity suggests preservation. At the same time, other developments reinforced the holographic idea. Gerard T. Hooft and Leonard Susskind proposed that all the information contained within a volume of space might be encoded on its boundary. This was radical. It suggested that the universe might be fundamentally holographic. That three-dimensional reality could emerge from two-dimensional information encoding. Black holes were central to this proposal because their entropy scales with area, not volume. Area scaling hints that the fundamental degrees of freedom reside on surfaces. If this is true, then the event horizon might not simply hide information. It might store it. But this did not resolve the paradox immediately. How exactly does information escape during evaporation? Does it leak out gradually? Does it remain until late stages and then burst out? Does the horizon become unstable? Each proposal introduced new complications. Some suggested the existence of firewalls, energetic barriers at the horizon that would burn infalling observers, violating the equivalence principle. Others resisted that idea, preserving smooth horizons but modifying entanglement structures. The debate grew technical and fierce. But at its core, it remained simple. Black holes force us to confront the meaning of information in physics. If information is preserved, then reality has a deep, unbreakable consistency. If it is not, then physical law contains irreducible gaps. And that gap would appear precisely where gravity is strongest. The stakes could not be higher. Because black holes are not rare curiosities. They populate nearly every galaxy. They are fundamental actors in cosmic evolution. If they destroy information, the universe forgets. If they preserve it, then the universe has a memory structure more subtle than spacetime itself. By the early 21st century, the consensus began to shift. Most theoretical physicists came to believe that information is preserved. Not because a complete proof existed, but because abandoning unitarity seemed too costly. The weight of quantum theory was too strong. The more promising route was to modify our understanding of spacetime. And that path would lead toward the idea that spacetime geometry is not fundamental. That information may be more primary than matter. And that black holes, rather than being destroyers, are translators. They do not erase. They transform. But the mechanism of that transformation remains one of the deepest open problems in theoretical physics. The war between relativity and quantum mechanics has not ended. But black holes have forced them into confrontation. And in that confrontation, something extraordinary is emerging. The possibility that information, not particles, not fields, not even spacetime, is the most fundamental ingredient of reality. By the late 20th century, something remarkable had happened. The black hole information paradox was no longer just a puzzle about collapsing stars. It had become a mirror reflecting the unfinished structure of physics itself. Because if information truly cannot be destroyed, then black holes cannot be what classical general relativity says they are. And if black holes are not what we thought, then spacetime itself may not be fundamental. This is where the problem stops being about astronomy and starts becoming about ontology. What is reality made of? For centuries, physics operated under a comfortable hierarchy. Matter was fundamental. Particles were the building blocks. Fields filled space. Spacetime was the stage on which everything unfolded. But the information paradox disrupts that hierarchy. Because it suggests that the preservation of quantum information is more fundamental than spacetime geometry. Let's unpack why. In classical general relativity, spacetime is smooth and continuous. The event horizon is a sharply defined boundary. Nothing crosses outward. Inside and outside are separated by absolute causal structure. But quantum mechanics does not treat boundaries as sacred. It treats states as entangled. Quantum systems are defined by correlations. If two particles are entangled, their states are linked regardless of distance. Information is not localized in simple ways. It exists in relational structure. Now imagine a black hole forming from a complex quantum state. That state is entangled with the rest of the universe. If the black hole evaporates completely, and if the final radiation is purely thermal, then those entanglements are broken. But quantum mechanics forbids breaking entanglement without preserving correlations somewhere. So where are they? One possibility is subtle correlations in Hawking radiation. The radiation may appear thermal at first glance, but at extremely fine-grained levels, it could contain hidden structure. Tiny deviations from perfect randomness. Patterns in entanglement. These patterns would not be obvious. They would not resemble the original system in any intuitive way. But in principle, the full quantum state of the radiation would contain all the information that fell in. This idea became formalized in what is called the Page curve. Don Page showed that if information is preserved, the entropy of Hawking radiation must initially increase as the black hole emits radiation, but eventually decrease as correlations begin encoding interior information outward. The entropy curve must rise and then fall. If Hawking radiation is perfectly thermal forever, the entropy only rises. That signals information loss. But if it deviates later, the entropy turns over. Recent theoretical work suggests that the Page curve can indeed emerge from a deeper quantum gravitational treatment. And that is a powerful clue. Because it suggests Hawking's original calculation was incomplete, not wrong, but missing the full quantum geometry. But to make that work, something profound must be true. The event horizon cannot be a perfect classical barrier. Information must be encoded at or near the horizon in a way that allows eventual release. This leads to a radical possibility. The event horizon behaves like a quantum membrane, a dynamic surface storing information in microscopic degrees of freedom. This is deeply connected to the holographic principle. The holographic principle proposes that all information contained within a volume of space can be described by degrees of freedom living on the boundary of that space. For black holes, this idea is not speculative. Their entropy scales with area, not volume. That alone suggests that the fundamental bookkeeping of information happens on surfaces. If this principle is universal, then our three-dimensional world may be a projection of more fundamental boundary information. Spacetime, in this view, is emergent. It is not the base layer of reality. It arises from quantum entanglement patterns. And black holes reveal this because they are the most extreme environments where geometry and information collide. If spacetime emerges from entanglement, then destroying information would unravel geometry itself. The stability of spacetime depends on information preservation. This is not poetic metaphor. It is becoming a technical insight. Research in quantum gravity suggests that spacetime connectivity, the very notion that one region is connected to another, may arise from entanglement structure. In some formulations, reducing entanglement weakens spacetime connectivity. Increase entanglement, and geometry strengthens. If that is true, then information is not merely content within spacetime. It is the fabric that builds spacetime. Black holes therefore do not sit within spacetime as destructive anomalies. They probe the limits of how spacetime emerges from information. And when Hawking radiation is reanalyzed with full quantum gravitational corrections, something fascinating appears. Information does not disappear. It becomes encoded in non-local correlations. This challenges classical intuition. Because classical thinking assumes locality. Causes produce effects nearby. Signals propagate at finite speed. But quantum mechanics has always challenged strict locality. Entanglement is inherently non-local. Black holes force us to reconcile non-local quantum information with local spacetime geometry. And in doing so, they suggest that locality itself may be emergent. Consider what this means. If information is never lost, then even the most violent gravitational collapse does not erase reality's bookkeeping. Every quantum state leaves a permanent imprint in the total wave function of the universe. Nothing vanishes without trace. Not stars. Not galaxies. Not civilizations swallowed whole. The matter can be destroyed. But the informational content is preserved in transformed form. This reframes black holes entirely. They are not cosmic erasers. They are information processors. They absorb structure and later re-express it through radiation, scrambled beyond recognition, but not annihilated. And this is where the story becomes philosophical. Because if information is more fundamental than matter, then reality is not built from stuff. It is built from relationships, correlations, patterns. The universe becomes less like a machine made of parts and more like a vast informational network. In that network, black holes are not endpoints. They are nodes. Extremes where the underlying informational architecture becomes visible. The information paradox therefore performs a strange inversion. It begins as a threat to physics. It becomes evidence that our deepest intuitions about spacetime are incomplete. And it points toward a future theory where gravity and quantum mechanics are unified not by forcing one into the framework of the other, but by recognizing that both emerge from something deeper. That deeper layer may be quantum information itself. This shift is profound. For centuries, physics asked, what is matter made of? Atoms, protons, quarks, fields. Now it asks, what are the laws of information that give rise to matter and spacetime? Black holes are the testing ground for that question. Because they force the issue. Either information is destroyed, and the universe has cracks in its consistency, or information survives, and spacetime is not fundamental. Increasingly, evidence points toward the second. But accepting that conclusion requires rethinking what we mean by reality. If spacetime emerges from entanglement, then geometry is not the base layer. If horizons encode information, then boundaries are more fundamental than volumes. If black holes evaporate without information loss, then even the most extreme destruction preserves structure at a deeper level. And that leads to a striking realization. Black holes do destroy matter. They crush atoms. They tear apart stars. They erase visible complexity. But they do not destroy the informational content of those systems. Reality does not forget. It transforms. The paradox is not a failure of physics. It is a signal. A signal that the next revolution in understanding will not merely adjust equations. It will redefine what we consider fundamental. Matter may be secondary. Spacetime may be emergent. Information may be primary. And black holes, once seen as the ultimate voids, may instead be windows into the most foundational layer of the universe. We began with the belief that black holes were simple, featureless, final. Now we see they are thresholds, where our classical intuitions fail, where quantum law insists on preservation, where geometry bends under the weight of information. This completes part 1. We have moved from classical certainty to quantum crisis, to the beginning of a deeper framework. When Stephen Hawking announced in 1974 that black holes radiate, the scientific world reacted with disbelief. Black holes were defined by their darkness. Their defining feature was that nothing escapes. And yet Hawking showed, using quantum field theory in curved spacetime, that black holes are not perfectly black. They glow. Faintly. Slowly. But inevitably. To understand why this was revolutionary, we need to look more closely at what Hawking actually calculated. In quantum field theory, empty space is not empty. Even in a vacuum, quantum fields fluctuate. Particle-antiparticle pairs constantly appear and annihilate within tiny fractions of a second. Normally, these virtual pairs leave no observable trace. They borrow energy briefly from the vacuum and return it almost immediately. But near an event horizon, the situation changes. Because the event horizon divides spacetime into two regions. Outside. Inside. And this boundary alters the behavior of quantum fields. When a pair of virtual particles forms near the horizon, one may fall inward while the other escapes outward. To a distant observer, It appears as though the black hole has emitted a particle. But this emission is not classical radiation. It is a quantum effect. And it comes at a cost. The particle that falls inward carries negative energy relative to the outside universe. That negative energy effectively reduces the black hole's mass. Energy conservation is preserved. The escaping particle carries positive energy outward. The black hole shrinks slightly. This process repeats. Over unimaginably long timescales, the black hole loses mass. Eventually, it evaporates. Mathematically, Hawking derived a temperature. T equals hc cubed, 8 gmk. The temperature is inversely proportional to mass. Large black holes are extremely cold. A solar mass black hole has a temperature far below the cosmic microwave background. It absorbs more radiation than it emits. But a tiny black hole would be extremely hot. The physics was stunningly elegant. It unified gravity, quantum mechanics, and thermodynamics. It confirmed Bekenstein's insight that black holes have entropy proportional to horizon area. And yet, hidden inside that beauty was a problem. The radiation is thermal. This means it has no memory of the internal state. It depends only on macroscopic parameters. Mass, charge, spin. It does not encode the detailed quantum configuration that formed the black hole. That conclusion seemed unavoidable in Hawking's semi-classical treatment. But something subtle was being assumed. The calculation treated spacetime geometry as classical. It quantized the fields on that background, but it did not quantize spacetime itself. The horizon was treated as a fixed geometric structure. This assumption may seem harmless. But it is precisely where the information paradox hides. Because the thermal nature of Hawking radiation arises from tracing out the degrees of freedom inside the horizon. In quantum mechanics, when you ignore part of a system, when you trace over inaccessible degrees of freedom, the remaining system appears mixed. Thermal. Random. But that does not mean the full system is random. It only means you are looking at part of it. In Hawking's calculation, the radiation outside the horizon is entangled with modes inside the horizon. When you trace over the interior, because you cannot observe it, the exterior appears thermal. But what happens if the interior disappears when the black hole evaporates completely? Now the entanglement has nowhere to reside. If the interior truly vanishes, the exterior radiation remains in a mixed state. A pure initial quantum state evolves into a mixed final state. That violates unitarity. But what if the tracing operation was incomplete? What if the horizon itself must be treated quantum mechanically? What if the interior is not permanently inaccessible in the way classical geometry suggests? This is where modern developments enter. In recent years, theoretical breakthroughs using quantum gravity techniques have shown that Hawking's original calculation must be modified when considering the full quantum gravitational path integral. One of the most important tools in this development is the concept of quantum extremal surfaces. Without diving too deeply into the mathematics, the idea is this. When calculating entropy of Hawking radiation in a fully quantum gravitational setting, one must consider contributions not only from the radiation outside but also from certain regions inside the black hole that become entangled in subtle ways. These interior regions, called islands, effectively transfer information into the radiation. The calculation produces a page curve. At early times, radiation entropy increases, matching Hawking's prediction. But after the page time, roughly halfway through the evaporation process, entropy begins to decrease. This means information is gradually encoded in the radiation. The black hole does not release information immediately. It releases it slowly, through delicate entanglement restructuring. This result is profound. Because it shows that when gravity itself is treated quantum mechanically, the information paradox can be resolved, at least mathematically. The radiation is not perfectly thermal after all. It contains correlations. Tiny deviations from randomness. These correlations are unimaginably subtle. For an astrophysical black hole, detecting them is completely impractical. But in principle, they exist. This shifts the narrative dramatically. Hawking radiation is not merely random emission. It is entanglement redistribution. The black hole acts as a quantum system whose degrees of freedom are gradually transferred to outgoing radiation. Information is not lost. It is re-expressed. But this resolution requires something radical. It requires accepting that spacetime geometry is not fixed. It must fluctuate. It must participate in entanglement. The event horizon is not a sharp classical wall. It is a quantum interface. And that leads to a deeper realization. Black holes are not objects sitting inside spacetime. They are manifestations of quantum gravitational degrees of freedom. Their entropy reflects microscopic configurations of spacetime itself. If spacetime has microstates, if geometry is built from quantum bits, then the horizon area measures the number of those bits. When matter falls in, it alters the configuration. When radiation escapes, it carries information about that configuration change. The process is subtle, non-local, but consistent. This perspective reframes the black hole entirely. It is not a destructive singularity. It is a highly compressed information storage device. It absorbs quantum states. It scrambles them. It later releases them in encoded form. From the outside, it looks simple. But beneath the surface, an immense informational computation unfolds. And this is where intuition fails. Because classical intuition expects locality. Signals move through space. Boundaries separate inside and outside. But quantum gravity suggests that locality itself may be emergent. Information can reorganize in ways classical geometry cannot represent. The paradox arose because we tried to force quantum mechanics into a classical spacetime box. When spacetime itself becomes quantum, the contradiction dissolves. But something extraordinary replaces it. Information is not merely conserved. It is the engine that shapes geometry. Black holes do not destroy information. They reveal how deeply information and spacetime are intertwined. The radiation that emerges is not a random afterthought. It is the final chapter of a quantum process that began with collapse. The apparent thermal nature was a mirage of incomplete treatment. Once the full quantum gravitational structure is included, the mirage fades. What remains is a universe where unitarity survives. Where information is never erased. Where even the most violent gravitational collapse cannot tear holes in the fabric of quantum law. This does not mean we fully understand the mechanism. Far from it. The island formula works in simplified models. A complete quantum gravity theory remains elusive. But the direction is clear. Hawking radiation was never the final word. It was the beginning of a deeper understanding. The black hole does not simply radiate heat. It radiates entangled history. And in doing so, it teaches us that the universe may be far more informationally structured than classical physics ever imagined. If black hole entropy scales with area rather than volume, something is wrong with our intuition. In every ordinary physical system, entropy scales with volume. More space means more room for microscopic configurations. A gas in a larger container has more possible arrangements than the same gas in a smaller one. Entropy increases with volume because degrees of freedom lie throughout the interior. But black holes break this pattern. Their entropy is proportional to the area of the event horizon, not the volume enclosed within it. Double the radius, and the area increases by the square. The volume increases by the cube. Yet entropy follows the square, not the cube. This is not a minor anomaly. It is a structural clue. It suggests that the fundamental degrees of freedom responsible for black hole entropy do not live in the volume. They live on the surface. That observation led Gerard T. Hooft and Leonard Susskind to propose something radical in the 1990s. The holographic principle. The idea is simple in statement, revolutionary in implication. All the information contained within a region of space can be described by information encoded on its boundary. The interior is not fundamental. The boundary is. To understand why this is so extraordinary, consider a hologram. A hologram is a two-dimensional surface that encodes three-dimensional information. When illuminated correctly, it produces the illusion of depth. The three-dimensional image is not stored in the volume. It is encoded in interference patterns across the surface. Now imagine that our universe works similarly. The three-dimensional world we experience could be a projection of information stored on a lower dimensional boundary. Black holes are where this idea becomes unavoidable. If you attempt to pack too much information into a volume, gravity prevents it. The region collapses into a black hole, and the maximum entropy it can contain is determined by the area of its boundary, not its volume. This implies a fundamental limit. Nature does not allow more than roughly 1 bit of information per Planck area. This is known as the Bekenstein bound. It sets a ceiling on how much information any region of space can contain. And that ceiling scales with area. This is not an abstract constraint. It is a physical law emerging from the combination of quantum mechanics and gravity. Now step back. If the maximum information inside a region scales with its surface, then perhaps the surface description is complete. Perhaps the interior description is redundant. This idea received powerful support from string theory. In 1997, Juan Maldacena proposed a concrete realization of holography known as the ADS-CFT correspondence. In simple terms, he showed that a theory of gravity in a higher dimensional spacetime can be mathematically equivalent to a quantum field theory without gravity on its boundary. A gravitational universe in 5 dimensions can be dual to a non-gravitational quantum theory in 4 dimensions. 2 different descriptions. Same physics. This was stunning. It suggested that gravity itself might be emergent from quantum degrees of freedom living on a lower dimensional surface. Spacetime geometry could arise from entanglement structure in a boundary theory. In this framework, black holes become even more fascinating. Their entropy corresponds to the number of microstates in the boundary theory. Their evaporation corresponds to unitary evolution in the boundary quantum system. Information never leaves the system. It is preserved in the lower dimensional description. The paradox dissolves because the boundary theory is manifestly unitary. There is no room for information loss. And if the boundary description is complete, then the bulk, the higher dimensional spacetime, must also preserve information. This changes how we think about space. Instead of space being fundamental, it may be a derived concept, emerging from patterns of entanglement. Some researchers have shown that the geometry of spacetime, distances, curvature, connectivity, can be reconstructed from entanglement entropy. In certain simplified models, changing entanglement strength changes the geometry. Less entanglement means regions pull apart. More entanglement means they connect more strongly. Spacetime, in this view, is woven from quantum correlations. Black holes are not disruptions of spacetime. They are extreme reorganizations of entanglement. When matter falls in, entanglement patterns shift. When radiation escapes, entanglement redistributes. The page curve calculations mentioned earlier rely heavily on holographic ideas. They show that when gravity is treated fully quantum mechanically, the entanglement entropy of radiation follows the expected unitary curve. Information is preserved because the boundary description enforces it. This suggests that black holes do not destroy information because the universe does not allow it. Information conservation is deeper than geometry. It is built into the quantum structure from which geometry emerges. But this perspective carries enormous philosophical weight. If our universe is holographic, then what we perceive as three-dimensional space may not be the ultimate level of reality. The depth we experience could be emergent. Just as temperature emerges from molecular motion. Just as fluid behavior emerges from atomic interactions. Spacetime may emerge from quantum information. And black holes are where that emergence becomes visible. When entropy saturates the area bound, spacetime can no longer accommodate more information in the interior. It reorganizes into a horizon. The horizon is not merely a barrier. It is a bookkeeping surface. An informational ledger. Every Planck scale patch encodes a quantum degree of freedom. These degrees of freedom account for the entropy. They evolve unitarily. They store the information of everything that falls in. When the black hole evaporates, that information flows back out. Not as a simple reconstruction of the original matter, but as subtle correlations in radiation. The destruction of matter remains real. Atoms are crushed. Stars are shredded. But the informational content is not erased. It is redistributed across the cosmic wave function. This realization reframes the entire black hole story. The classical picture described them as cosmic sinks, places where complexity ends. The holographic picture describes them as translators, places where complexity changes representation. Matter becomes geometry. Geometry becomes radiation. Information flows through transformations but is never annihilated. And if this is true, then information is not just a conserved quantity. It is the substrate of reality. Mass and energy curve spacetime. But perhaps entanglement builds spacetime. Black holes test that idea at the limits. They push geometry to extremes. They saturate entropy bounds. They reveal that area, not volume, governs informational capacity. This is not speculative fantasy. The mathematics of holography works with extraordinary precision in certain theoretical models. While our universe is not exactly the same as those models, the lessons appear robust. Information conservation is compatible with black hole evaporation. Spacetime can emerge from entanglement. The paradox dissolves not by destroying quantum mechanics, but by elevating information above geometry. And this is where the narrative shifts from resolution to revelation. If the universe is holographic, then what we call matter is secondary. What we call space is derivative. What we call black holes are boundary phenomena. The deepest layer may not be particles or fields, but quantum information. And black holes, once feared as destroyers of everything, may instead be proof that the universe never forgets. They are not holes in reality. They are windows into its informational core. When we say that information is preserved, we are making a claim more radical than it first appears. We are not merely saying that quantum states evolve predictably. We are saying that the universe has a deeper layer of consistency than spacetime itself. Because if spacetime were fundamental, truly fundamental, then it would have the authority to erase. An event horizon would be absolute. A singularity would be final. A boundary would be unbreakable. But the information paradox shows that spacetime does not have that authority. When spacetime geometry seems to demand erasure, quantum mechanics refuses. And quantum mechanics wins. This means something extraordinary. Spacetime is not the deepest level of description. It is an emergent structure. To understand this, let's strip away intuition. What do we actually mean by space? We mean separation. Distance. The idea that two things can be near or far. But quantum entanglement ignores classical distance. Two particles can be separated by billions of light-years and still behave as a unified system. Their correlations do not weaken with distance. Distance does not define relationship. Entanglement does. Now imagine that entanglement is not just something happening inside spacetime. Imagine it is what builds spacetime. In holographic models, researchers have demonstrated that spatial geometry can be reconstructed from entanglement entropy. The mathematical relationship is precise. Change entanglement structure, and the geometry changes accordingly. If entanglement between two regions decreases to zero, the geometry connecting them collapses. They become disconnected. In other words, entanglement is connectivity. Connectivity is geometry. Geometry is space. This means space is not a background. It is a manifestation. A large-scale approximation of a deeper informational network. And black holes sit exactly at the limit of this network. A black hole is what happens when entanglement density saturates its maximum allowed value. The Bekenstein bound tells us that no region of space can contain more than roughly 1 bit of information per Planck area. If you try to exceed that bound, space-time rearranges itself. It forms a horizon. A boundary. An informational compression surface. The horizon is not merely a geometric surface. It is an entropic limit. It marks the point where informational density becomes maximal. Now think about evaporation. If a black hole were simply a geometric object, its disappearance could destroy information. But if it is an informational structure, a compression of entanglement, then evaporation must be an informational redistribution. And that is exactly what modern calculations show. When the page curve is derived from quantum gravitational methods, the entropy of radiation rises and then falls. That fall is not magic. It is entanglement restructuring. Interior degrees of freedom become encoded in radiation correlations. This is not classical communication. It is quantum redistribution. The global wave function remains pure. And here is the key shift. The interior of the black hole and the exterior radiation are not separate realities. They are two descriptions of a single informational system. The classical picture assumes inside and outside are independent. Quantum gravity suggests they are dual, complementary, two perspectives on one underlying state. This challenges locality, but it does not violate causality. Because causality, like locality, may itself be emergent. We assume causality is fundamental because it appears stable in everyday life. Cause precedes effect. Signals propagate at finite speed. But if spacetime emerges from entanglement, then causality may be a statistical property of large entanglement networks. At microscopic scales, informational relationships are primary. Causal structure emerges when those relationships stabilize into geometric form. Black holes destabilize that form. They push entanglement to extremes. They saturate bounds. They reveal that classical spacetime is an approximation. And when that approximation fails, information remains consistent while geometry bends. Now consider time. We treat time as a flowing dimension. Past becomes present. Present becomes future. But in quantum mechanics, the fundamental equations are time-symmetric. The Schrödinger equation does not distinguish past from future. Entropy gives time direction. But entropy itself is informational. If spacetime emerges from entanglement, then time may also emerge from entropic gradients. In this view, black holes are extreme time distorters. They maximize entropy density. They stretch classical time near horizons. They compress it near singularities. But at the informational level, evolution remains unitary. The global state does not flow in time the way classical intuition suggests. It evolves as a whole. This is a subtle but profound shift. Instead of imagining the universe as a movie playing frame by frame inside spacetime, we may need to imagine it as a quantum informational object whose apparent geometry unfolds from correlations. Black holes are where the illusion cracks, where the smooth movie glitches, where the underlying code briefly becomes visible. And what does that code insist upon? Information conservation. Always. Even when stars collapse. Even when singularities form. Even when matter disappears. Because matter is not fundamental. It is a pattern within the informational substrate. Destroy the pattern, and the material configuration vanishes. But the informational relationships that defined it remain embedded in the global structure. Scrambled. Transformed. But preserved. This is why the statement black holes destroy matter, but not information is so powerful. It draws a boundary between classical identity and quantum consistency. Matter is classical. Information is quantum. Matter is emergent. Information is fundamental. A black hole can obliterate atomic structure. It can dismantle molecular organization. It can erase classical form. But it cannot erase the quantum correlations that define that form. Those correlations become woven into the radiation, encoded across spacetime, invisible to classical eyes, but present in the wave function. This means destruction is not absolute. It is representational. The representation changes. The substrate persists. This realization transforms black holes from monsters into messengers. They do not punch holes in physical law. They test its resilience. And the law holds. Unitarity survives. Information survives. Spacetime adjusts. What we once feared as annihilation becomes transformation. And this forces us to reconsider what existence means. If existence is informational, then identity is pattern. Destroy the pattern's physical form, and identity seems gone. But the pattern's informational trace remains embedded in the total state of the universe. Black holes are the crucible of that truth. They are not endings. They are compressions. Phase transitions in geometry. where entanglement density peaks, where classical description breaks. But informational consistency endures. The paradox did not expose a flaw in physics. It exposed a flaw in our intuition. We assumed spacetime was fundamental. We assumed geometry was ultimate. But black holes teach us that geometry bends to protect information, not the other way around. And that may be the deepest insight of all. The universe is not built from space and matter. It is built from quantum information. Space is the large-scale behavior of entanglement. Time is the thermodynamic gradient of informational states. Matter is localized excitation within that network. Black holes are the stress test. And the test result is clear. Matter can be destroyed. Information cannot. Because information is not something inside the universe. It is what the universe is made of. For decades, the black hole information paradox felt like a distant storm. You could hear it. You knew it was there. But it stayed on the horizon. Hawking had argued that black holes destroy information. Others argued they must not. The disagreement was serious, but it felt abstract. Until the paradox stopped being abstract. Until it became mathematical. Until it forced a direct contradiction. That moment came in 2012. The AMPS paper did not introduce new speculative physics. It simply combined three assumptions that physicists already believed were true. That was the brilliance. And the danger. The assumptions were simple. Quantum mechanics is unitary. Information is never destroyed. Effective field theory works near the horizon. Physics there looks smooth. The equivalence principle holds. Falling into a black hole should feel ordinary at the horizon. Individually, these are foundational. Together, they cannot coexist. To see why, we must reconstruct the logic carefully. Start with Hawking radiation. Near the event horizon, quantum fluctuations create particle-antiparticle pairs. One falls in. One escapes. The escaping particle becomes Hawking radiation. The pair is entangled. That entanglement is essential. Without it, the vacuum near the horizon would not look smooth. Quantum field theory tells us that the vacuum state requires correlations between inside and outside modes. This is not optional. It is built into how quantum fields behave. Now introduce the page time. The page time is the moment when a black hole has radiated roughly half its entropy. Before that time, the radiation entropy increases. After that time, if information is preserved, the entropy must decrease. Because the radiation must begin purifying itself. The total system, black hole plus radiation, must remain in a pure quantum state. This means that late radiation must be entangled with early radiation. Not with the interior, but with the previously emitted quanta. Here is the collision. Take a late Hawking particle. Call it B. According to effective field theory, B must be entangled with its interior partner A. That ensures smooth spacetime at the horizon. But according to unitarity and the page curve, B must also be entangled with the early radiation R. Because only that entanglement allows the total radiation to purify. Quantum mechanics forbids this. Entanglement is monogamous. If B is maximally entangled with A, it cannot also be maximally entangled with R. This is not philosophical. It is mathematical. It comes from strong subadditivity of entropy. The inequality cannot be violated. So B cannot be fully entangled with both. One entanglement must break. If B remains entangled with A, information is lost. If B becomes entangled with R, the A or B entanglement must break. And breaking that entanglement destroys the smooth vacuum at the horizon. Because the smooth vacuum depends on those correlations. Remove them, and the vacuum becomes excited. Instead of empty space, there is high-energy radiation. Not gentle crossing, but violent incineration. A firewall. This was shocking because it attacked the equivalence principle directly. Einstein's greatest insight was that locally, gravity is indistinguishable from acceleration. That free fall feels normal. The firewall says no. At the horizon, something dramatic happens. The equivalence principle fails. Spacetime is not smooth. For decades, Physicists had believed that large black holes had gentle horizons, that you could cross without noticing. The AMPS result said that belief cannot coexist with information preservation. This was not a speculative idea. It was a logical trap. No exotic assumptions. No wild extensions. Just accepted physics, combined carefully. And the result was devastating. You must sacrifice something fundamental. The community fractured. Some physicists embraced firewalls. They argued that the equivalence principle is approximate, that quantum gravity effects must appear at the horizon, that smooth geometry cannot survive once information demands new entanglement patterns. Others resisted deeply. Abandoning the equivalence principle felt like heresy. General relativity had survived every experimental test. Gravitational waves. Time dilation. Black hole imaging. It worked. How could it fail so dramatically at a horizon? Black hole complementarity was the proposed shield. Complementarity argued that no observer sees a contradiction. From outside, information is reflected in radiation. From inside, spacetime remains smooth. No single observer can compare both stories. Therefore, no paradox manifests physically. It was clever. It protected both relativity and unitarity. But AMPS argued that entanglement structure creates an observer-independent contradiction. The paradox was not about perspective. It was about entropy inequalities. Complementarity alone could not escape the trap. This was the turning point. Before AMPS, the information paradox felt like a question about singularities. After AMPS, it became a question about horizons. About local physics. About the nature of spacetime itself. And here is where the deeper insight began to emerge. The conflict was not between quantum mechanics and gravity. It was between entanglement and geometry. Smooth spacetime requires specific entanglement across the horizon. Information preservation requires different entanglement across radiation. Geometry assumed entanglement patterns that quantum consistency refused to allow. The geometry had to adapt. Or collapse. This is when holography returned as more than a mathematical curiosity. ADSA CFT had already shown that gravity in a volume can be equivalent to a non-gravitational quantum theory on its boundary. In that boundary theory, unitarity is obvious. There is no information loss. Black holes are just thermal states. The paradox disappears. But what about the interior? How does a smooth spacetime emerge from a unitary boundary theory? The answer seemed to lie in entanglement. Researchers began to see that entanglement structure determines geometry. Not metaphorically. Literally. The Ryu-Takayanagi formula showed that entanglement entropy in the boundary theory corresponds to geometric areas in the bulk. Area equals entropy. Geometry equals information. This was not poetic. It was mathematical. And it suggested something radical. The interior of a black hole is not an independent region of spacetime. It is encoded in entanglement between degrees of freedom. When the page time arrives, that encoding shifts. The interior degrees of freedom become accessible in the radiation's entanglement wedge. This led to the development of the island formula. But before that resolution came tension. For a moment, it seemed possible that the universe demanded firewalls. That smooth horizons were illusions. That general relativity breaks violently at the boundary. This would have been a profound shift. It would mean that spacetime is not smooth at macroscopic scales. That black holes are surrounded by energetic membranes. But as calculations deepened, a different possibility emerged. The interior might not need to exist independently. It could be reconstructed from radiation. The geometry behind the horizon could be dual to correlations outside. This idea reframed the paradox. The problem was not that information escaped. It was that we misunderstood what inside means. If spacetime emerges from entanglement, then the boundary between inside and outside is not absolute. It is relational. And that is the heart of the lesson. Black holes do not break quantum mechanics. They reveal that spacetime is subordinate to entanglement. The AMPS paradox was terrifying because it forced us to admit that our most trusted pillars could not all stand simultaneously. But instead of collapsing physics, it pushed it deeper. It forced a re-evaluation of what geometry is, of what locality means, of what horizons represent. The firewall may not exist, but the crisis it created was necessary, because it exposed the hidden structure of reality. Spacetime is not a stage. It is a consequence. And when consequences conflict with fundamentals, consequences must yield. Information is fundamental. Geometry is negotiable. That is the shift AMPS initiated. Black holes are not contradictions. They are consistency checks. They push the universe to its edge. And the edge reveals the deeper rule. Matter can burn. Spacetime can stretch. Horizons can distort. But quantum information does not die. It reorganizes. And reality reshapes itself to protect it. After the firewall crisis, the situation looked bleak. Either spacetime burned at the horizon, or quantum mechanics failed, or effective field theory collapsed. For years, no one had a satisfying resolution. The paradox seemed locked. Then something unexpected happened. The solution did not come from new exotic particles. It did not come from observational breakthroughs. It came from entropy calculations. And from a deeper look at how we calculate quantum entanglement in gravity. The key concept is something called the entanglement wedge. To understand why this matters, we must first understand how entropy is computed in quantum systems. In ordinary quantum mechanics, if you divide a system into two parts, A and B, the entropy of A measures how entangled it is with B. If A and B are maximally entangled, the entropy is high. If they are independent, entropy is low. Now imagine that the system includes gravity. That changes everything. Because in gravity, space-time itself fluctuates. The geometry is not fixed. So when calculating entropy in a gravitational system, you cannot assume a fixed background. You must include gravitational contributions. This insight led to a refinement of the Ryu-Takayanagi formula. Originally, that formula said, the entanglement entropy of a boundary region equals the area of a minimal surface in the bulk divided by 4 times Newton's constant. Area equals entropy. But when quantum corrections are included, the formula changes. Instead of just area, you must add the entropy of quantum fields in the bulk region enclosed by that surface. And crucially, you must choose the surface that minimizes the total generalized entropy. This surface is called a quantum extremal surface. And the region enclosed by that surface is called the entanglement wedge. Now here is where everything shifts. When physicists applied this refined formula to evaporating black holes, they found something extraordinary. At early times, the entanglement wedge of the radiation includes only the radiation itself. The black hole interior is separate. Entropy rises. Everything behaves as Hawking predicted. But after the page time, something changes. A new extremal surface appears. And the entanglement wedge of the radiation suddenly expands. It includes part of what was previously considered the black hole interior. An island forms. This island is a region inside the black hole that is now included in the radiation's entanglement wedge. In other words, the radiation owns part of the interior. This is not metaphorical. It is a direct consequence of minimizing generalized entropy. The calculation shows that after the page time, including this island reduces the entropy of the radiation. And when the island is included, the page curve emerges correctly. Entropy rises, peaks, and then falls. Information is preserved. No firewall required. But what does this mean physically? It means that the interior of the black hole is not independent. After enough evaporation, the degrees of freedom describing the interior are encoded in the radiation. The inside is outside. The boundary between them dissolves. This is not information escaping through the horizon. It is a redefinition of where information resides. The paradox assumed that the interior was a separate region. That information inside could not be accessed by outside radiation. The island formula says that assumption is wrong. The interior is part of the radiation's entanglement structure. Spacetime boundaries are not absolute. They depend on entanglement. This is a profound shift. We tend to think of space as dividing reality into compartments. Inside the black hole, outside the black hole. But in quantum gravity, regions are defined by entanglement wedges, not by classical geometry alone. And those wedges change over time. This dissolves the AMPS contradiction. Because the outgoing Hawking particle does not need to be entangled with both the interior and the early radiation. The interior itself becomes encoded in the radiation. There is no independent A system competing with R. The geometry reorganizes. The entanglement structure reshapes spacetime. Information is preserved without violating monogamy. No firewall. No loss of unitarity. But at a cost. The cost is that spacetime is not fundamental. It is emergent. And its regions are defined by quantum information flow. The island formula tells us something almost unbelievable. The radiation far away from the black hole contains the interior in its entanglement wedge. If you had complete quantum control over the radiation and infinite computational power, you could reconstruct information that was once behind the horizon. This does not mean you could jump into the black hole. It does not violate causality. But it means the interior is not an inaccessible vault. It is encoded non-locally. The black hole is not a prison. It is a phase of entanglement. Now consider what this means for destruction. When matter falls into a black hole, it crosses the horizon. Classically, it is gone. But quantum mechanically, its information becomes scrambled. It mixes with interior degrees of freedom. As evaporation proceeds, those scrambled correlations migrate into the radiation's entanglement wedge. The information does not travel outward like a signal. It becomes re-represented in the entanglement network. This is not emission. It is reallocation. And that reallocation is what preserves unitarity. The island formula was not guessed. It was derived from semi-classical gravity path integrals. Replica trick calculations revealed new saddle points in the gravitational action. These saddle points correspond to geometries with replica wormholes. These wormholes connect different copies of spacetime in the entropy calculation. They look bizarre, but they produce the correct page curve. And their interpretation suggests that entanglement reshapes geometry itself. Wormholes are not shortcuts for travel. They are manifestations of entanglement structure in the gravitational path integral. Geometry is influenced by information. This flips our classical hierarchy. We thought geometry was primary. We thought matter and information lived inside it. But black holes show that geometry responds to informational constraints. The universe refuses to allow information loss. And to preserve that rule, spacetime adjusts. The horizon is not a hard boundary. It is a feature of a specific entanglement configuration. As that configuration changes, so does the effective boundary. The island formula is not just a solution to a paradox. It is a revelation. It reveals that locality is conditional. That interior and exterior are relational. That entropy defines geometry. And that black holes are not erasers of information. They are redistributors of it. For decades, the information paradox seemed to threaten quantum mechanics. Then it seemed to threaten general relativity. The island formula suggests that neither must fall. But our picture of spacetime must change. Black holes do not destroy information. They redefine where it lives. Matter is destroyed. Structure collapses. But the informational pattern survives in correlations that stretch across spacetime. Even when the black hole evaporates completely, the final radiation state encodes the initial information. Hopelessly scrambled. But intact. The universe does not forget. This solution is not universally accepted. There are debates. Questions remain about how exactly the interior emerges. About computational complexity. About practical reconstruction. But the entropy calculations are robust. The page curve emerges. And that changes everything. Because the page curve is not philosophical. It is quantitative. It says information preservation is not optional. It is encoded in the structure of quantum gravity. The island formula is a turning point. It transforms black holes from paradox generators into consistency enforcers. They force us to abandon naive locality, to abandon rigid boundaries, to accept that spacetime regions are defined by entanglement, not geometry alone. And this carries a final implication. If the interior of a black hole can be encoded in radiation outside, then spacetime itself is a kind of error-correcting code. This idea has gained traction. Quantum error correction models of ADS CFT show that bulk geometry can be reconstructed redundantly from boundary degrees of freedom. Information is protected not by isolation, but by encoding. Black holes are not exceptions to this. They are extreme examples. Matter falls in. Information is encoded in the bulk, then re-encoded in radiation. Never lost. Always preserved within the total quantum state. Black holes destroy matter. They do not destroy information. Because information is not a substance to be burned. It is the relational structure of the universe. And relational structure cannot simply vanish. It can only transform. The island formula did not make black holes less mysterious. It made them deeper. They are no longer holes in space. They are entanglement engines. Testing the flexibility of geometry. Forcing spacetime to adapt. And proving that the deepest rule of reality is not geometric. It is informational. The universe protects information so fiercely that it will rewrite its own geometry to preserve it. That is not poetic exaggeration. That is what the equations show. And that is why black holes do not destroy information. They force us to understand what information truly is. The island formula gave us something extraordinary. It showed that information is preserved. That the page curve works. That unitarity survives. But it also created a new tension. Because preservation is not the same thing as recovery. A book thrown into a black hole is not erased. Its quantum information is scrambled. Encoded into Hawking radiation. Distributed across correlations. But can it be reconstructed? That question opens a new frontier. And it introduces something physicists rarely discuss outside specialist circles. Computational complexity. The difference between what is possible in principle and what is achievable in practice. Imagine you collect every Hawking photon emitted by a black hole. You wait billions of years. You capture every quanta of radiation. In theory, the full quantum state of that radiation encodes the information of everything that fell in. But extracting it would require performing an incredibly precise quantum computation. Not a classical calculation. A quantum one. On a system with astronomical Hilbert space dimension. Let's slow down and understand why. When matter falls into a black hole, its quantum state becomes entangled with the black hole's internal degrees of freedom. As the black hole evaporates, those internal degrees of freedom become entangled with outgoing radiation. But the entanglement is not neat. It is chaotic. Black holes are believed to be the fastest scramblers in nature. Scrambling means that information injected into the system becomes distributed across all degrees of freedom extremely quickly. Not destroyed, but spread out. This scrambling time is proportional to the logarithm of the black hole's entropy. For astrophysical black holes, this time is surprisingly short. A black hole does not lazily mix information. It violently disperses it across its entire state space. By the time radiation carries information outward, that information is not localized. It is encoded in subtle correlations between enormous numbers of particles. This is where complexity enters. To reconstruct the original state, one would need to decode these correlations. But decoding requires reversing a highly complex unitary transformation. And that transformation grows exponentially with the system's entropy. The entropy of a solar mass black hole is around 10 to the power of 77 in dimensionless units. The Hilbert space describing it is unimaginably vast. The number of possible quantum states exceeds any classical number you could write down. Even if information is preserved, retrieving it requires computational resources beyond any realistic capacity. There is a distinction in physics between information being destroyed, information being inaccessible. The island formula ensures it is not destroyed. Complexity theory suggests it may be forever inaccessible. This was emphasized by researchers studying quantum chaos and black hole dynamics. Black holes behave like random unitary operators. From the outside, the outgoing radiation appears almost thermal. The deviations that encode information are tiny, subtle, hidden in high-order correlations. If you look at individual photons, they appear random. The information is not in the particles. It is in their joint quantum state. Reconstructing that joint state is equivalent to solving a problem that may require time exponential in the entropy, which could exceed the age of the universe. This introduces a powerful philosophical shift. Even if information survives, it may be practically erased. Not fundamentally gone, but functionally irretrievable. This distinction matters. Consider a scrambled egg. The laws of physics allow you to reverse every particle's motion and reconstruct the egg. But in practice, that is impossible. The information is preserved in microscopic correlations. But retrieving it requires control beyond imagination. Black holes are scrambled eggs on cosmic scale. The universe does not violate quantum mechanics, but it may impose computational barriers so extreme that recovery is impossible. Some physicists call this computational censorship. Nature may protect certain information not by destroying it, but by making its retrieval exponentially hard. This idea connects to the Hayden-Preskill protocol. Hayden and Preskill asked, if you throw a quantum diary into an old black hole, one past the page time, how quickly does information come back out? Their analysis suggested something surprising. After scrambling time, information thrown into an old black hole can begin to emerge in radiation quickly. This suggests that black holes act like mirrors for new information once they are sufficiently evaporated. But this does not mean recovery is easy. It requires having detailed knowledge of the black hole's quantum state and performing highly complex decoding operations. In principle, information escapes. In practice, no observer could decode it without immense quantum computational power. And that leads to a deeper realization. Black holes do not simply test physics. They test the limits of knowledge. There may be truths that are preserved in the structure of reality, yet forever beyond practical access. The island formula shows that interior information becomes part of the radiation's entanglement wedge. But entanglement wedge reconstruction is not trivial. It relies on quantum error correction. Bulk information is redundantly encoded in boundary degrees of freedom, but extracting it requires precise decoding. Without that decoding, the radiation looks random. The book is gone. The matter is gone. Only with extraordinary computational resources could one reconstruct it. This blurs the line between destruction and concealment. If something can never be retrieved, is it meaningfully preserved? Physics answers yes. Philosophy hesitates. Because for observers, inaccessible information might as well be destroyed. But the universe does not operate on observer convenience. It operates on consistency. Quantum mechanics demands unitarity. Even if the price is computational intractability. This introduces another layer to the black hole story. The universe may not violate its fundamental rules, but it may hide their consequences behind complexity walls. Information is conserved, but buried in correlations too intricate to unravel. Black holes are maximal scramblers. They approach what is called quantum chaos. Their dynamics resemble random matrices, which means small perturbations grow rapidly. Information disperses across all degrees of freedom. This scrambling is not optional. It is intrinsic to their thermodynamic nature. Entropy is enormous. Microstates are vast. The black hole interior is not orderly. It is maximally mixed. So when evaporation begins transferring information outward, that information is encoded in extremely subtle statistical deviations from perfect thermality. The page curve tells us entropy eventually decreases. But the radiation never looks simple. It always appears random unless you examine enormous correlations. This is where the computational barrier becomes fundamental. Some researchers argue that recovering information from Hawking radiation would require time exponential in the black hole's entropy. For astrophysical black holes, this exceeds the lifetime of the universe by unimaginable margins. So while information is not destroyed, it is effectively hidden forever. And that is a remarkable compromise. Nature preserves consistency, but not accessibility. The paradox is resolved at the level of fundamental law, but not at the level of practical recovery. This also reframes the emotional narrative of black holes. They are not shredders of information. They are encryptors. They transform simple structure into maximal entanglement. The book you threw in is not burned. It is encrypted into the quantum state of the cosmos. No key. No shortcut. Only the original unitary evolution, too complex to reverse. This encryption analogy is not metaphorical. Black hole dynamics resemble quantum chaotic circuits. Information spreads rapidly across the system. After scrambling, local measurements reveal nothing. Only global measurements recover correlations. And global measurements on Hawking radiation are beyond realistic possibility. So the final picture becomes layered. Level 1, classical intuition, matter is destroyed. Level 2, quantum mechanics, information is preserved. Level 3, complexity theory, information is practically irretrievable. Each layer corrects the previous one, but none completely erases it. Matter truly is destroyed. The structure of atoms collapses. The physical object disappears. But the informational content of that object remains encoded. And retrieving it is computationally prohibitive. Black holes do not annihilate information. They transform it into a form so scrambled that it becomes effectively inaccessible. This is not a flaw. It may be a fundamental feature of quantum gravity, a balance between consistency and concealment. And that leads to a final insight in this section. The paradox forced us to ask whether information survives. The answer appears to be yes. But it also forced us to confront something else. The universe may preserve information even when no observer could ever retrieve it. Reality is not obligated to be knowable. It is only obligated to be consistent. Black holes satisfy that obligation. They obey unitarity. They obey entropy laws. They obey quantum gravity constraints. But they also demonstrate that preservation does not imply transparency. Matter can vanish. Information survives. But in a form so scrambled that it might as well be hidden in the fabric of spacetime itself. Black holes do not destroy information. They bury it in complexity. And that is almost as unsettling. Let us begin with something simple. If black holes cannot destroy information, then there is no known process in nature that can. Not supernovae. Not particle annihilation. Not evaporation. Not collapse. Every known interaction, no matter how violent, is described by a unitary transformation of quantum states. The form changes. The arrangement changes. But the total informational content does not disappear. This is not poetic language. It is a structural property of quantum theory. The wave function evolves reversibly. Always. Even when it appears irreversible to us. That word, irreversible, is where the tension lies. Because our world feels irreversible. Ice melts. Stars burn out. Civilizations collapse. Black holes form. Everything moves forward. Entropy increases. But entropy increase does not mean information loss. It means information dispersal. Entropy is a measure of how many microstates correspond to a macrostate. When a system becomes more disordered, its information is not destroyed. It becomes harder to access. Black holes are the ultimate example of this. Throw a library into a black hole. The pages burn. The atoms disintegrate. The structure collapses. From the outside, it appears erased. But quantum mechanics insists that the information content, the precise arrangement of those atoms, is still encoded somewhere in the global state. Scrambled beyond recognition. But not deleted. Now extend that logic. If no process erases information, then the universe accumulates informational history. Every interaction leaves a trace. Every quantum event contributes to entanglement patterns. The past is not wiped away. It is embedded in correlations. We usually imagine the universe as evolving moment to moment. But quantum mechanics describes the entire system with a single wave function evolving unitarily. Nothing is discarded. There is no delete function. Black holes tested whether that rule has exceptions. They do not. Which suggests something profound. The universe behaves like a memory system. Not a memory in the conscious sense, but a memory in the structural sense. Information is stored, encoded, transformed, but not annihilated. This reframes destruction itself. When we say something is destroyed, we mean its macroscopic form disappears. But microscopically, the information describing it remains in correlations between particles. When you burn paper, the words are gone. But the information is embedded in the motion of molecules, the distribution of photons, the arrangement of ash. It is not practically recoverable. But it is physically present. Black holes are the most extreme case. They scramble information into nearly maximal entropy states. Yet even they cannot eliminate it. This suggests that information is more fundamental than matter. Matter can be rearranged, annihilated, converted to radiation. But information persists as relational structure. And if information persists universally, then perhaps information is the foundation upon which physical reality is built. This idea is not fringe. Some of the deepest theoretical work in modern physics points toward an informational ontology. John Wheeler once proposed the phrase "it from bit." The idea that physical reality arises from informational yes-no distinctions. That the universe at its core is not made of substance, but of information. Black holes strengthen that intuition. They reveal that information is not optional. Even when geometry collapses, information remains consistent. This forces us to reconsider what is primary. Is spacetime the stage upon which information exists? Or is spacetime itself a manifestation of informational relationships? Holographic duality suggests the latter. Spacetime geometry emerges from entanglement entropy. Connectivity arises from correlations. Locality arises from stable entanglement patterns. If this is true, then the universe is not a container for information. It is an informational structure whose large-scale behavior appears as spacetime. Black holes are where that structure is stress-tested. They push informational density to its limit. They compress entropy to maximal values. And yet the informational substrate survives. Even singularities, once thought to represent physical breakdown, are now viewed as limits of geometric description, not informational annihilation. The singularity may be replaced by quantum gravitational processes. But those processes remain unitary, consistent, informationally intact. This perspective dissolves an ancient fear. For centuries, philosophers wondered whether there are true endings. Whether destruction can be absolute. Whether annihilation exists at a fundamental level. Quantum mechanics answers no. There is transformation. There is scrambling. There is dispersal. But not deletion. Black holes were the last possible exception. They are not. And this raises a deeper possibility. If the universe preserves information perfectly, then the total state of the universe contains the imprint of every event that has ever occurred. Not accessible. Not readable. But encoded. This is not mysticism. It is a direct implication of unitarity. The global wave function evolves. It never collapses in a fundamental sense. Even measurement, in some interpretations, is entanglement with environment. Information is redistributed. Never erased. Now consider the cosmological implications. If the universe began in a low-entropy state and evolved unitarily, then the entire history of the cosmos is embedded in its quantum state. Galaxies forming, stars igniting, life emerging, civilizations rising, all encoded in correlations. Black holes, far from being erasers of cosmic history, are integrators of it. They absorb structure, scramble it, then re-emit it as radiation, returning information to the cosmos in disguised form. This suggests that the universe is a closed informational loop. Nothing leaves. Nothing disappears. Everything transforms. But is this truly comforting? There is something unsettling about it. Because if information is never destroyed, then the universe never forgets. Every quantum interaction leaves a trace in entanglement, even if that trace becomes practically impossible to decode. Reality may be fundamentally archival, a cosmic ledger that never deletes entries. This is not mystical permanence. It is structural permanence. Information conservation is a symmetry of quantum law. Black holes confirmed it under the most extreme conditions imaginable. Now let's confront the final layer. Does preserved information imply recoverable identity? If a person were to fall into a black hole, their informational pattern would not be destroyed, but it would be scrambled into radiation over billions of years. Does that count as survival? Physics does not answer questions of identity. It answers questions of consistency. The pattern persists, but not in recognizable form. The distinction between preservation and persistence of identity remains philosophical. Yet the physics is clear. Annihilation is not fundamental. Only transformation is. And black holes, once feared as cosmic obliterators, are proof. They cannot erase the informational structure of what they consume. They can only hide it, scramble it, re-encode it. In doing so, they reveal something astonishing about the universe. Information is not a secondary property of matter. It is the invariant quantity underlying physical law. Matter is dynamic. Energy converts. Geometry curves. But information remains conserved. This may be the deepest symmetry of reality, more fundamental even than energy conservation. Because energy conservation arises from time symmetry, information conservation arises from quantum unitarity. And quantum unitarity appears universal. Black holes tried to break it. They failed. Instead, they exposed how spacetime must reorganize itself to protect it. The island formula showed geometry yielding to entanglement. The computational barrier showed preservation without accessibility. The AMPS paradox showed that geometry must adapt or collapse. All of it points in the same direction. The universe protects information at all costs. If this is true, then the final image of a black hole changes completely. It is not a cosmic shredder. It is an informational transformer. Matter falls in. Correlations rearrange. Radiation emerges. Nothing is erased. The surface of the black hole, the horizon, encodes entropy proportional to its area. Area measures information capacity. Geometry becomes bookkeeping. The universe tracks its informational content through spacetime curvature. Black holes are not holes. They are memory compression devices. They pack maximal information into minimal area, then slowly decompress it, never losing a single bit. And this may be the final implication. The universe is not made of stuff. It is made of relationships. Quantum information is the relational structure. Spacetime is the emergent scaffolding. Black holes are the test case. And the test result is clear. Matter can be destroyed. Structure can collapse. Form can vanish. But information, the relational pattern that defines structure, is never annihilated. The universe does not forget. It transforms. And that transformation is not arbitrary. It is governed by unitarity, by entropy bounds, by entanglement geometry. Black holes did not reveal a flaw in physics. They revealed a deeper layer beneath spacetime, an informational foundation. And once you see that, the title becomes more than a statement. It becomes a principle. Black holes destroy matter. But information is never lost. Because information is not inside the universe. It is what the universe is made of. For most of the 20th century, black holes were described with a single word: destruction. They were the ultimate endpoint. The cosmic eraser. The place where matter vanished and the laws of physics collapsed. If you asked a physicist in the 1970s what happens at the center of a black hole, the honest answer would have been uncomfortable. The equations predict a singularity, a point of infinite density, infinite curvature, a place where spacetime ends. Even the phrase itself, ends, carried a tone of finality. It suggested something absolute. And that idea was terrifying. Because physics is built on continuity, on predictability, on transformation. A singularity was different. It was not a transformation. It was a breakdown. The mathematics simply stopped. And for a long time, people interpreted that mathematical breakdown as physical annihilation. If a star collapses beyond its Schwarzschild radius, it forms an event horizon. Cross that boundary and nothing escapes. Not light. Not matter. Not information. That last word, information, was added almost casually at first. But it would become the central issue. In classical general relativity, information does not even exist as a fundamental quantity. The theory describes geometry. Mass curves spacetime. Spacetime tells matter how to move. There is no concept of quantum state preservation in Einstein's equations. So when matter falls into a black hole and disappears behind the horizon, classical physics has no problem with that. The information about its internal configuration is simply inaccessible. And if a singularity forms, it may be destroyed entirely. There is nothing in classical gravity that forbids it. The problem emerged when Hawking combined gravity with quantum mechanics. His 1974 calculation showed that black holes are not perfectly black. They emit radiation. Slowly. Relentlessly. They evaporate. And when Hawking calculated the properties of that radiation, it appeared purely thermal. Random. Uncorrelated. Which meant the radiation contained no information about what formed the black hole. If a complex object collapses into a black hole and the black hole evaporates into featureless thermal radiation, the information describing that object is gone. Not scrambled. Gone. This was not a minor inconsistency. It was catastrophic. Quantum mechanics is built on unitarity, the principle that the evolution of a closed system preserves information. If black holes destroy information, then quantum mechanics is wrong, or incomplete, or approximate. For decades, this seemed plausible. Maybe gravity modifies quantum mechanics. Maybe singularities are true erasers. Maybe unitarity fails in extreme conditions. The image of the black hole as annihilator persisted. Popular science amplified it. Documentaries described singularities as places where physics breaks down, where time ends, where reality tears. The black hole became the ultimate symbol of cosmic oblivion. But beneath the drama, physicists were uneasy. Because information loss is not a small violation. It is a structural collapse. Quantum theory is not a collection of independent rules. It is a tightly woven mathematical framework. If unitarity fails, conservation of probability fails. Predictability fails. The entire structure becomes unstable. And so the debate intensified. Some argued that information truly is destroyed. Others insisted that quantum mechanics must survive. Gradually, evidence accumulated on one side. Not experimental evidence. We cannot probe black hole interiors directly. But theoretical consistency evidence. Holographic duality suggested that gravity in certain spacetimes is equivalent to ordinary quantum field theory without gravity. And in that boundary description, unitarity is explicit. There is no room for information loss. Black holes correspond to thermal states. But thermal states still evolve unitarily. This was a powerful hint. Then came the island formula. The entropy calculations. The Page curve. And slowly, the community shifted. Black holes do not destroy information. The singularity is not an eraser. The horizon is not a shredder. Instead, black holes scramble information. They encode it in subtle correlations. They redistribute it. But they do not annihilate it. This required a reframing. The black hole is not a cosmic trash bin. It is a thermodynamic object. It has entropy proportional to its horizon area. It obeys laws analogous to thermodynamics. Temperature, entropy, energy conservation. And when it evaporates, those laws must be consistent with quantum mechanics. The myth of destruction arose from conflating inaccessibility with annihilation. If we cannot retrieve something, we assume it is gone. But physics does not operate on human accessibility. It operates on mathematical consistency. Information can be hidden beyond practical recovery and still be preserved in principle. Black holes are the ultimate demonstration of that distinction. Consider what destruction really means. When a building burns, we say it is destroyed. But the atoms remain. The energy radiates outward. The structure changes form. Nothing fundamental disappears. Black holes extend this idea to its limit. They destroy macroscopic form. They dissolve structure completely. But the quantum information describing that structure survives in the global wave function. The difficulty is not that information vanishes. It is that it becomes entangled with degrees of freedom beyond our ability to decode. This reframes singularities as well. For decades, the singularity was treated as the ultimate endpoint. But modern quantum gravity research suggests singularities, artifacts of classical theory. When quantum effects are included, the infinite curvature may be replaced by finite processes. Loop quantum gravity proposes bounces. String theory proposes fuzzballs. Holography suggests interior reconstruction from boundary states. None of these pictures include true information annihilation. The singularity, once feared as a physical abyss, is increasingly seen as a sign that classical geometry is incomplete. Not that reality ends. This is a subtle but profound shift. We once imagined black holes as failures of physics. Now we see them as confirmations of its deepest rule. Information conservation survives even there. The event horizon does not mark the end of law. It marks the limit of classical description. Beyond that, quantum entanglement reorganizes geometry itself. This forces a conceptual hierarchy. For centuries, geometry felt fundamental. Space was the stage. Time was the flow. Matter moved within it. Black holes challenge that hierarchy. They reveal that geometry can bend, stretch, evaporate, even collapse, yet information persists. Which implies that information is deeper than geometry, deeper than spacetime. Black holes are not cosmic exceptions. They are extreme test cases. And they pass the test. Matter falls in. Entropy increases. Radiation emerges. Information remains encoded. Never deleted. The old narrative of annihilation collapses. What remains is transformation. But that transformation is not arbitrary. It obeys strict mathematical rules. Unitarity. Entropy bounds. Entanglement structure. Black holes force us to confront a mature view of destruction. At the macroscopic level, destruction is real. The star is gone. The structure is gone. But at the fundamental level, destruction is a reorganization of degrees of freedom. Nothing more. Nothing less. The black hole, once imagined as the universe's most violent eraser, becomes something else entirely. A mirror. Reflecting our misunderstanding of what is fundamental. We thought matter was fundamental. We thought geometry was fundamental. We thought singularities were endpoints. We were wrong. The deeper invariant is information. And black holes, far from contradicting that principle, enforce it. They reveal that even when space-time contorts beyond recognition, the informational structure of reality remains consistent. That is not dramatic. It is disciplined. It is not mystical. It is mathematical. And it replaces fear with clarity. Black holes do not destroy information. They never did. They exposed the limits of our classical intuition. And forced us to see what was always true. Destruction is not fundamental. Transformation is. And the universe, even at its most extreme, remains internally consistent. That is what we thought black holes were. Annihilators. Endings. Breakdowns. What they turned out to be is something far more interesting. They are guardians of consistency. Stress tests of physical law. And proof that even in the darkest regions of spacetime, information is never lost. If black holes cannot destroy information, then information must be more fundamental than matter. That statement sounds philosophical. It is not. It is a structural consequence of modern physics. For centuries, matter was treated as the primary substance of reality. Atoms were the building blocks. Solid particles existing in space. Then quantum mechanics arrived and dissolved that picture. Atoms are not solid. They are mostly empty space. Electrons are not tiny spheres orbiting nuclei. They are excitations of quantum fields. And quantum fields themselves are not little vibrating strings in space. They are mathematical objects defined over spacetime. The more we refine our understanding of matter, the less substantial it becomes. What we call a particle is not a tiny object. It is a localized excitation of an underlying field. And that field is described by a wave function, a complex mathematical structure encoding probabilities and correlations. The electron is not a thing. It is a pattern, a stable excitation within a field. Matter, at its deepest level, is not substance. It is structure. And structure is informational. To describe a particle fully, you must specify its quantum state. Spin, momentum, position probabilities, entanglement with other systems. That specification is information. Remove the informational description, and there is no particle, which means matter does not exist independently of informational structure. Now consider what happens when matter falls into a black hole. The classical form is destroyed. The star collapses. Atoms disintegrate. But the informational description of those excitations, the full quantum state, evolves unitarily. It is transformed, not erased. This means matter is not what survives fundamental processes. Information is. Matter is a temporary configuration of information, an arrangement, a pattern of correlations. When that pattern changes, matter appears destroyed. But the underlying informational relationships persist in new forms. This is not speculation. It is the unavoidable interpretation of quantum field theory. Quantum mechanics does not describe little billiard balls moving through space. It describes wave functions evolving in Hilbert space. Hilbert space is not a place. It is a mathematical structure encoding possible states. And those states are defined by information. The deeper we look, the less material reality appears. Fields replace particles. Wave functions replace trajectories. Entanglement replaces independence. Now add gravity. General relativity tells us that mass and energy curve spacetime. But what is mass in quantum field theory? It is a parameter describing excitations of fields, which means spacetime curvature responds to informational patterns within quantum fields. Gravity couples to information. This becomes clearer in holographic duality. In certain models, a higher dimensional gravitational spacetime emerges from a lower dimensional quantum field theory without gravity. The geometry of the bulk corresponds to entanglement patterns in the boundary theory. Change entanglement. Geometry changes. Which means spacetime curvature, what we interpret as gravity, is shaped by informational relationships. Black holes are the most extreme demonstration of this. Their entropy is proportional to horizon area. Not volume. Area. That suggests that the information content of a region scales with its boundary, not its interior. This holographic scaling implies that the interior description is redundant, encoded on the boundary, which again suggests that geometry is emergent from information. If spacetime geometry can be derived from entanglement entropy, then matter and gravity are not fundamental building blocks. They are effective descriptions of deeper informational structure. This reverses classical intuition. We once believed information was a property of matter. Now it appears matter is a manifestation of information. Black holes force this conclusion. Because if matter were fundamental and information secondary, then black holes could destroy information by destroying matter. But they do not. Matter dissolves. Information persists. Therefore information is deeper. Now consider energy. Energy conservation arises from time translation symmetry. It is a powerful principle. But energy can transform. Mass becomes radiation. Radiation becomes particles. Nothing about energy conservation implies preservation of form. Information conservation is different. It preserves the full quantum state structure, not just scalar quantities. Unitarity ensures that the wave function evolves reversibly, which means every quantum amplitude carries history. Matter is temporary. Information is invariant. This suggests that reality is not built from particles. It is built from relationships. Entanglement is the glue. Two particles can be separated by enormous distances and still behave as one system. Their correlation is not mediated by classical signals. It is a property of their shared quantum state. If entanglement defines relationships, and relationships define structure, then matter is relational. Not intrinsic. Not isolated. The electron in your body is not an independent object. It is part of a vast entanglement network stretching across the universe. Black holes amplify this insight. When matter falls into a black hole, its informational pattern becomes entangled with the entire system. As the black hole evaporates, that information is distributed into radiation, encoded in correlations across spacetime. There is no central repository of matter, only evolving informational patterns. This aligns with quantum error correction perspectives in holography. Bulk spacetime information is redundantly encoded in boundary degrees of freedom, meaning the same informational content can be reconstructed from different subsets of the system. This redundancy suggests robustness. Reality protects information by distributing it across relational networks. Matter is not a solid core. It is a code word in a quantum error correcting code. Destroy the local structure. The global encoding survives. Black holes do not delete code words. They redistribute encoding, which raises a profound possibility. Perhaps what we call matter is simply a stable pattern in the informational substrate of the universe. Like a standing wave in a fluid. The fluid is the underlying quantum field. The wave is matter. Disrupt the wave. The fluid remains. The pattern changes. But the informational description of the fluid state evolves consistently. This perspective dissolves the notion of absolute solidity. There are no tiny hard objects at the bottom of reality. There are only stable configurations of information. Quantum fields. Entanglement networks. Hilbert space states. Black holes prove that these configurations can be destroyed at the macroscopic level without violating fundamental informational rules. Matter is not primary. Information is. And if information is fundamental, then spacetime itself may be secondary. As we saw earlier, geometry can emerge from entanglement entropy. Connectivity corresponds to correlation strength. Distance may reflect entanglement structure. In that picture, matter is excitation within emergent geometry. And geometry is a manifestation of information. The hierarchy flips. Information, entanglement, geometry, matter. Black holes operate at the boundary of this hierarchy. They compress matter to extreme densities. They push entanglement to maximal entropy. They test whether geometry can collapse without breaking informational consistency. It cannot. Geometry adapts. Information remains intact. This suggests a radical ontology. Reality is informational at its core. Matter is not the bedrock. Spacetime is not the bedrock. Information is. And black holes are the experiment that confirmed it. This does not mean reality is a simulation. It does not imply digital physics in a simplistic sense. It means that the invariant quantity preserved under all transformations is informational structure. Particles appear and disappear. Fields fluctuate. Stars collapse. But the full quantum state evolves reversibly, which means that at the deepest level, existence is about relational configuration, not substance. Black holes clarified this. They removed the last plausible mechanism for information annihilation. And in doing so, they forced us to recognize that matter is not the ultimate layer of reality. It is an emergent pattern in a deeper informational substrate. That substrate obeys unitarity. It preserves correlations. It enforces entropy bounds. It shapes geometry. And matter is one of its expressions. If information is fundamental, then the universe is not made of stuff. It is made of structure. And structure persists even when stuff dissolves. Black holes destroy matter. They do not destroy the structure that defines it. Because structure is encoded in quantum information. And quantum information is the invariant backbone of physical law. There is a subtle distinction we have been circling for hours. Black holes do not destroy information. That is the conclusion modern physics increasingly supports. But there is a second question hiding beneath it. If information is preserved, does that mean it can be known? Preservation and accessibility are not the same, and the difference between them may define the limits of knowledge itself. When a black hole evaporates, the information about everything that fell into it is encoded in Hawking radiation. That statement is now mathematically defensible. The Page curve supports it. The island formula supports it. Holography supports it. But suppose you collect every photon of that radiation. Suppose you store it in a perfect quantum memory. Could you reconstruct the object that fell in? In principle, yes. In practice, almost certainly not. The reason is not energy. It is not distance. It is complexity. The information is not sitting neatly in individual particles. It is encoded in correlations among vast numbers of degrees of freedom. To decode it would require reversing an unimaginably complex unitary transformation, one whose computational cost may exceed the lifetime of the universe. This introduces a profound limit. There are truths about the universe that are physically preserved but computationally inaccessible. Reality may contain information that no observer can ever retrieve. Not because it was erased, but because it is hidden behind combinatorial barriers. This reframes the meaning of irreversibility. In everyday life, processes appear irreversible. A cup shatters. Ash scatters. Smoke disperses. We say these events cannot be undone. But at the microscopic level, the laws are reversible. The apparent irreversibility arises from entropy increase, from the growth of inaccessible correlations. Black holes are the extreme case of this principle. They do not violate reversibility. They magnify it into inaccessibility. The information about the shattered cup still exists in the precise motion of particles. But reconstructing it requires tracking every microscopic degree of freedom. Black holes elevate this to cosmic scale. They scramble information so thoroughly that practical recovery becomes impossible. This leads to a difficult realization. The universe may preserve more than we can ever know. There may be no fundamental information loss. But there may be permanent epistemic loss. Knowledge loss. From the perspective of observers embedded in spacetime, the island formula tells us that information behind the horizon becomes part of the radiation's entanglement wedge. But entanglement wedge reconstruction requires precise decoding operations. Without the correct decoding map, the radiation looks random, meaning that even though the information is there, it is not accessible. The difference between exists and can be known becomes critical. Physics traditionally aims at predictive power. We build theories to forecast outcomes. But black holes expose a deeper question. Is the universe obligated to make its information accessible, or only to preserve it consistently? The evidence suggests the latter. Quantum mechanics enforces consistency, not transparency. And this changes how we interpret finality. For centuries, singularities symbolized absolute endings. The collapse of law, the erasure of history. Now we know that singularities likely mark the limit of classical geometry. Not informational annihilation. But something else has replaced the fear of destruction. The recognition of concealment. Black holes do not end information. They hide it behind complexity walls. This is not just a feature of black holes. Complexity barriers appear throughout physics. In chaotic systems. In quantum many-body dynamics. In cosmology. There may be states that are mathematically reversible but practically irreversible. Which means that even in a deterministic universe, prediction and reconstruction can be fundamentally limited. Not because the laws fail, but because computation becomes intractable. This suggests that knowledge itself may have structural limits. Even if the universe is perfectly consistent, it may not be fully knowable. Black holes sharpen this tension. They show that preservation does not guarantee recovery, that the universe does not delete information, but neither does it promise accessibility. This challenges an implicit assumption of science. We often assume that if something exists physically, it can in principle be measured or reconstructed. Black holes suggest otherwise. There may be information that exists in the wave function but is forever beyond operational reach. Consider what this means for the concept of history. If the universe preserves all quantum information, then the complete past is encoded in the present state. But decoding that past may be computationally impossible. The past is not erased. It is buried in entanglement. This makes time feel different. We experience time as a sequence of events that leave traces. But at the quantum level, the total state contains correlations across time. Irreversibility is emergent, not fundamental. Black holes intensify this. They represent regions where entropy saturates bounds, where scrambling is maximal, where the illusion of finality is strongest. Yet even there, unitarity holds, which means that what feels like obliteration is only concealment. This leads to a sobering conclusion. The universe is not obligated to make itself legible. It is obligated only to obey its laws. Information conservation is one such law. Accessibility is not. We may live in a cosmos where information survives every process. But practical reconstruction is impossible beyond certain complexity thresholds. This has implications beyond black holes. It affects how we think about cosmology, about the early universe, about inflation, about quantum fluctuations stretched across cosmic scales. Those fluctuations are still encoded in the cosmic microwave background, but their precise quantum microstructure is beyond recovery. The information exists in principle, but not in practice. Black holes are the most dramatic example of this pattern. They are nature's encryption devices. They take structured input and produce scrambled output. The encryption key is the exact unitary evolution of the system. But calculating that key requires solving dynamics exponentially complex in entropy, which may exceed the computational capacity of the universe itself. There is an irony here. The paradox began as a fear that information might be destroyed. It evolved into the realization that information is preserved. And now it culminates in a quieter recognition. Preserved information may be forever beyond retrieval. The universe is consistent, but not necessarily transparent. This reframes destruction. From the standpoint of observers, something can be effectively destroyed even if it is fundamentally preserved. A message encoded in random noise is still there. But without the decoding algorithm, it is indistinguishable from nothing. Black holes turn messages into noise, not by erasing them, but by distributing them across enormous entanglement networks, which suggests a limit not of physics, but of epistemology. There are events whose detailed microstructure will never be known, not because the universe deleted them, but because decoding them requires resources beyond any possible observer. This humbles our understanding of knowledge. Science aims to uncover laws, not necessarily to decode every state. Black holes remind us that the universe may contain preserved histories inaccessible to any intelligence. Information may survive, but awareness of it may not. This does not undermine physics. It strengthens it, because it shows that consistency does not imply convenience. The laws of quantum mechanics do not guarantee that information will be recoverable. They guarantee only that it will not be erased. Black holes test this distinction at the highest possible level. And the result is clear. The universe does not allow annihilation, but it does allow concealment, which means that finality, the sense that something has absolutely ended, is an illusion born of limited perspective. From the viewpoint of fundamental law, there are no true endings. Only transformations into states too complex to reverse. Black holes do not represent the death of information. They represent the boundary between what exists and what can be known. And that boundary may be one of the deepest limits in nature. For most of human history, destruction meant disappearance. When something burned, it was gone. When something collapsed, it ended. When something fell beyond reach, it was lost forever. That intuition shaped how we understood the universe. Stars died. Civilizations vanished. Matter dissolved. And when black holes entered scientific awareness, They seemed to represent the ultimate form of erasure. A place where even light could not escape. A cosmic furnace that swallowed everything. The word singularity only intensified that image. Infinite density. Infinite curvature. A terminal point. The end of physics. The end of history. But what we have uncovered over the last half-century forces a radical revision. Black holes do not represent annihilation. They represent transformation under extreme law. The fear was that black holes might destroy information. That the universe, under certain conditions, might allow history itself to be deleted. But the equations resisted that conclusion. Quantum mechanics refused to bend. Unitarity held firm. And the deeper we investigated, the more the same answer returned. Information is never lost. Matter is rearranged. Energy is redistributed. Space-time may curve, twist, even evaporate. But the informational structure describing reality evolves consistently. No event deletes the past. Even when that past seems sealed behind a horizon. This realization changes more than black hole physics. It changes how we understand reality itself. Because if information cannot be destroyed, then nothing is ever truly erased. Not fundamentally. Every interaction leaves correlations. Every collapse encodes structure. Every particle that enters a black hole contributes to the entanglement pattern that defines its radiation. The universe is not a system that forgets. It is a system that scrambles. And scrambling is not annihilation. It is concealment. We once believed black holes were cosmic shredders. Now we understand they are cosmic encryptors. They do not burn history away. They encode it into degrees of freedom so subtle, so widely distributed, that recovery becomes practically impossible. But not fundamentally forbidden. That distinction is everything. Because it means the universe does not permit true finality. The death of a star is not the deletion of its existence. Its atoms become new structures. Its radiation carries memory of its thermodynamic state. Its gravitational imprint shapes spacetime around it. Even a black hole's evaporation leaves behind encoded correlations reflecting its formation. The cosmos is not a sequence of disappearances. It is a continuous rewriting of structure. Nothing vanishes. It only changes form. This is not poetic language. It is the mathematical architecture of quantum theory. The Schrödinger equation is reversible. The wave function evolves without collapse at the fundamental level. Even apparent collapse in measurement reflects entanglement with environment. Information spreads. It does not die. Black holes were the ultimate test of that principle. If information could disappear anywhere, it would be there, inside the most extreme gravitational structure the universe allows. But it does not disappear. The paradox forced us to confront that. Hawking radiation once seemed thermal and featureless. Now we understand that subtle correlations encode the missing structure. The page curve proved that entropy rises and then falls. Unitarity survives. The island formula revealed that interior regions contribute to radiation entropy. Holography showed that bulk geometry emerges from boundary information. Every path led to the same conclusion. Reality is built on preservation, not erasure. This means that even when matter is destroyed, its informational content persists. The structure that defined it evolves. It is never deleted. And that realization reframes destruction itself. Destruction is local. Information is global. When a book burns, its molecular structure is lost. But the correlations describing its state are redistributed into photons and ash. To us, it is gone. To the universe, it is transformed. Black holes operate on that same principle. They appear to swallow objects whole. But what they actually do is redistribute the information into horizon degrees of freedom and eventual radiation. From outside, it looks final. From the perspective of fundamental law, it is not. This challenges the intuitive meaning of loss. Because if nothing is ever truly erased at the deepest level, then finality becomes perspective dependent. We experience irreversibility because we cannot track all degrees of freedom. Entropy hides correlations. Complexity blocks reconstruction. But the underlying evolution remains consistent. The universe keeps perfect records. We simply cannot read them. Black holes dramatize that limitation. They show that preservation does not guarantee accessibility. But they also show that annihilation does not occur. There is a quiet reassurance in that. Not sentimental. Structural. Reality is not fragile in the way we once feared. It does not tear holes in its own history. It does not create regions where law collapses and information vanishes. It protects consistency even under the most extreme conditions imaginable. If anything could have broken the rules, it would have been black holes. But they did not. Instead, they revealed how deep those rules go. Which leads to a broader implication. If information is fundamental, then the universe is not made of objects. It is made of relationships. Particles are excitations. Fields are patterns. Spacetime geometry may emerge from entanglement. Matter is temporary structure within a deeper informational substrate. And that substrate does not permit deletion. This reframes existence. You are not merely a collection of atoms. You are a configuration of information. A specific pattern of correlations among quantum fields. That pattern evolves. It changes. But at the fundamental level, its informational description is preserved within the universal wave function. That does not mean individuality persists in any familiar sense. It does not imply personal immortality. But it does mean that nothing that occurs is fundamentally erased. Events alter structure. They do not create voids in law. The universe is consistent all the way down. Black holes proved that. And in doing so, they resolved one of the deepest fears in theoretical physics. The fear that reality might contain true annihilation. It does not. What it contains is transformation beyond comprehension. We began this journey with a simple but unsettling question. Do black holes destroy matter? The answer is yes. Matter in its familiar form does not survive. Stars collapse. Atoms disintegrate. Structures dissolve. But the deeper question was always this. Do black holes destroy information? And the answer, as far as our best theories can tell, is no. They do not. And if they cannot, nothing can. Because they are the most extreme environments permitted by physical law. If preservation holds there, it holds everywhere. That realization reshapes how we interpret the cosmos. Not as a theater of disappearance, but as a system of continual encoding. The universe is not careless with its history. It does not discard states. It evolves them. Black holes do not represent holes in reality. They represent the limits of classical description. And at those limits, quantum structure asserts itself. Consistency prevails. Nothing is ever truly lost. Only transformed into forms we may never be able to decode. That is not mystical. It is mathematical. It is the quiet power of unitarity. The universe remembers everything, even when we cannot. And that may be one of the most profound discoveries physics has ever made. Not that black holes are terrifying. Not that spacetime bends. But that at the deepest level, reality does not permit erasure. Only transformation. Only concealment. Only evolution of information under inviolable law. So the next time you hear that black holes destroy everything, remember this. They destroy structure. They do not destroy truth. They do not destroy history. They do not destroy information. They compress it. Scramble it. Encode it beyond recognition. But they do not erase it. Because the universe does not forget. It only transforms. And that distinction changes everything. If you stayed with me through this entire exploration, you now understand something most headlines miss. Black holes are not cosmic shredders. They are cosmic guardians of consistency. And the story is not about destruction. It is about preservation at a level deeper than matter itself. If this perspective shifted how you see the universe, consider subscribing. Not for sensational claims, but for careful journeys into what physics actually says, and what it does not. Because the real universe is always more subtle, more structured, and more astonishing than the simplified versions we inherit. And sometimes the most powerful discovery is not that something ends, but that nothing ever truly does.